Hello, everyone. Good morning. A very good turnout for the first session of the day. Welcome to the Trident stage. We're gonna be having a little bit of fun here, a little bit of energy going, and I am going to be your MC today. My name is Masha Healy, and I'm really excited to learn alongside with you guys today. So our first talk is going to be Kendall Cole, who is the director and co-founder of Proximity Labs. Kendall co-founded Proximity Labs, a research and development firm focused on the NEAR ecosystem. Formerly at Consensus and the NEAR Foundation, Kendall has a deep Web3 product and business development experience. Kendall leads strategy and outreach for NEAR's DeFi and scalability solutions. Let's hear what you have to say, Kendall.
Let's give this a second and see if we can load these slides. Where is my... All right, 1 second. Here we go. Okay, now we should be good. All right, hey everyone, my name is Kendall, and I'm going to talk to you guys about how you can build cross-chain applications without using bridges, which we think is going to be a pretty important pattern for this, this next wave of the market cycle. So this probably isn't a surprise to any of you who are already using DeFi, but cross-chain DeFi is becoming increasingly important pretty much every single day. So here's a chart that I found pretty interesting, which is that since November, we've seen daily bridge volumes more than 4x. And we've also seen cross-chain swap volumes see a similar kind of peak in interest. And it looks like this is only going to continue as we have more and more chains, layer 2s, and other kind of layers that are launching, which seems like pretty much hourly right now. One of the problems we have, though, is that bridges have a lot of limitations. They are really difficult to build securely. Just a few of the headlines from the last couple of years that show some of actually really high-quality teams and high-quality bridges that have suffered exploits. And a lot of times this is actually just because the attack surface of a bridge is quite large. They're really difficult to build. The other issue is that there are no bridges that support anywhere close to every single chain or layer. Even some of the more prolific bridges like Wormhole, which have done a great job of integrating a lot of chains, do not support nearly every single chain that's out there. And some chains they can't support, like non-smart contract chains, including Bitcoin and others. So what this means is that if you want to bridge across multiple chains, most likely you're going to have to use several different bridges, and each bridge has a completely different user experience. You might notice that bridges have very different speeds. Some are, minutes, some are hours, some are days or even weeks. You also might notice that when you bridge an asset to a chain, you'll realize that you actually ended up with the wrong version of the asset. A lot of bridges use kind of a wrapping, unwrapping pattern. And what this means is that you may end up with a certain type of wrapped USDT and go try to deposit that into a lending protocol or swap that somewhere and realize actually that you have a version that is either unsupported or does not have very much liquidity, which creates a pretty frustrating problem for you to then solve and figure out how to get the right asset. And then last but not least, bridges oftentimes do not provide you a great way to acquire the gas tokens of the chain that you are using. Some of them are starting to add this into their protocol, and it is helping. but you likely will still end up in a situation where you'll have to find a way to acquire the gas token for the chain you're trying to use, even if you manage to bridge, say, a stablecoin or another asset. And again, every single bridge is going to be different, and so users have to basically learn how to use several different bridges, which is not ideal. Fortunately, we actually do think that there is a new design pattern that is going to alleviate a lot of these challenges. And basically, this is what we call programmable MPC. So a lot of you might be familiar with MPC type of wallets. If you've ever used Coinbase Wallet, supports this. If you've used institutional grade solutions such as Fireblocks, they support this. But these are actually really designed for kind of the user having one of the keys, and then a centralized party having one of the keys. With programmable MPC, we can actually allow developers to kind of tap into these solutions as well, and we can also make them decentralized. So what are some of the key advantages of decentralized programmable MPC? Well, they can support any chain, including non-smart contract chains. So with this programmable MPC, you can support Bitcoin, you can support Ripple, you can support Dogecoin, you can support any chain, and you also get instant support for new chains. As the MPC kind of provider, what you do have to support is the different types of the different elliptic curves. So you need ECDSA for the EVM chains, Bitcoin, and a lot of Cosmos chains, and you need EDDSA for Solana, Near, Cardano, and others. But if you have those primitives, then you can support any new chain as soon as it launches without having to go and integrate that chain like most of the bridge providers have to. And then last but not least, you can provide a much more standardized user and developer experience because you can essentially have a simple API for developers to build on top of. They might still have to themselves integrate a new chain, but they'll be targeting a specific community anyway. And then users, when they go use this solution, they won't have to wait different amounts of times for bridging. They won't have to potentially even deal with gas tokens depending on the implementation. It can just be a lot more consistent and normalized for the user, which we think can lead to a true potential for something like chain abstraction, where the user doesn't even have to know which chain they're on. So there are several teams that are building programmable MPC today. I think just about 8 total, and probably a couple that I missed here. Fortunately, some very good ones. And there's 2 kind of main patterns that are arising. So the most common is what I call deposit-based. And this is typically where essentially like the programmable MPC network will maintain a single or a small number of deposit addresses that can basically be used to create kind of a canonical bridged asset. So good examples of this, Dfinity with their chain key, they have kind of Dfinity Bitcoin, Dfinity Ethereum. Zeta Chain recently launched, has been getting a lot of attention. They support Bitcoin and are going to be supporting more. They basically have this kind of main deposit address. Some of the more unique ones, Chainflip and Thorchain is kind of the OG here. They use this for like swap-based addresses, where like the kind of nodes will give you an address to deposit your Bitcoin or Ethereum to, and then they'll allow you to trade essentially that asset with another user. And then Axelar is building kind of more of a generalized bridge solution, but still has this very deposit-based, like they maintain one address for you rather than letting you have access to the address yourself. So Near Protocol, which is what we're working on, and then Lit Protocol use a little bit of a different pattern that I would call account-based. And what's cool about the account-based is it actually lets an end user maintain sub-accounts for any number of blockchains. So the example from what we're building in Near is we actually let this Near account, which can also be a smart contract, and that opens up a lot of really cool avenues, can essentially request through a smart contract, or even through like kind of a native Near action, can request that the Near validators or the MPC nodes sign an arbitrary payload, which will likely be a transaction for Bitcoin, for Ethereum, for OP, for Atom, whatever it might be. And then what they'll get back is they'll get back that signed payload, which they can then relay to the chain. And a lot of this will be abstracted away, and the user will just think they're signing normal transactions that'll end up on the Bitcoin chain, that'll end up on whatever destination chain they have. For developers, what's nice about this is the API is actually quite simple. It's basically going to be this sign function. They pass in the payload. They can also pass in kind of a key derivation path, which means that like every single Near account can have essentially like a very high number, sort of infinite number of accounts they can sign for on any given chain. So a Near account could have, say, 100 accounts on Bitcoin, or a smart contract that's using this in a more flexible way might have tens of thousands of accounts that they're maintaining on Bitcoin or on Ethereum or on these different chains. And then you can, of course, pass in the key type. And this is basically like how the only thing you really have to do to differentiate between chains is like make sure you're using ECDSA for ECDSA supported chains, make sure you're using ED25519 for those chains, etc. So to visualize a little bit of what this process looks like, so we have the near account. The near account initiates the signature, which goes to these MPC signing nodes. Then these MPC signing nodes basically sign this payload, and then they'll essentially help route this transaction to a destination chain, which can be several. We're also building a gas relayer on top of this, which is a similar type of path. The big difference here is that you'll have relayers who will essentially pick up, using like a gas router contract, these relayers will basically pick up the transaction. The user will pay them in something like USDC. Recently, we had a demo from the Sweatcoin team who had their users paying in Sweat to then send a transaction on Binance. And then this relayer will basically take your payment, send you BNB on your BNB address or Ethereum address, whatever it is, and then also will route your signed transaction. And a lot of times this can happen in the same block, and so it creates like a really smooth experience. And this actually enables wallets, application layer teams, end users to not have to deal with multiple gas tokens and multiple chains. They can actually live in a world where they can use USDC to pay for gas on transactions on any chain, which we think is pretty cool. So what are some of the other use cases? Well, we're particularly excited about what can happen when it's a smart contract that's using these chain signatures. So I think there's 3 in particular that I'm excited about, in addition to a couple of others that will eventually blow minds. First is bridgeless cross-chain DeFi, hence the name of this talk, and we'll go into a little bit more detail there. The second is DeFi on non-smart contract chains. So you can basically take chains that really only support transfers, like a Bitcoin, like a Doge, like a BitTensor. And what you can do is you can use near smart contracts to act as escrow contracts and also kind of manage who controls what. And on top of just this fairly simple primitive, you can build lending protocols that support any asset on any chain, including assets that are staked or in kind of unique states, maybe even in liquidity pools. It's very flexible. And you can also then, of course, build swaps. And you can actually power swaps between any asset on any chain. So you could be trading like a staked TIA for an NFT on Solana. It can get really wacky. And then the third that we'll touch on a little bit is what we were just discussing, which is that multi-chain account abstraction pattern, which includes support for a gas relayer. So one of the things that's cool about near accounts is they're natively smart contract accounts, meaning that like any near account can have any number of keys. And so you can rotate keys, which can add for security. You can have kind of multi-signer patterns. It's very flexible. And you get that out of the box. And you can then use that as your account to sign for any chain, which I think is pretty cool. So to dive a little bit deeper on some of the ideas that we're seeing teams explore in the bridgeless cross-chain DeFi realm. So we talked about the native swaps. We talked about the cross-chain lending order book. You can even power something like restaking for any asset on any chain. And you can basically handle kind of the slashing conditions and the reward conditions on near, which is going to open up a lot of opportunities and just ways to reuse assets. And then we'll walk through this example kind of specifically. But you can also build a Bitcoin ordinals marketplace that's quite trustless. So to dive a bit deeper into that example, let's imagine that we have a seller of an ordinal. We have a buyer who wants to pay, say, USDC in this case, for that ordinal. And then in the middle, we're going to have this near smart contract that's going to act as kind of the marketplace contract. So the way this will work first is the seller will basically ask the marketplace contract for a deposit address on Bitcoin. What's going to be unique about this Bitcoin account is that only the marketplace contract can request from the MPC signers the ability to send a transaction on behalf of this account. And what it'll do within the smart contract state is it'll basically recognize that the seller is the owner of this account, and thus that seller can like request to, say, withdraw or move their ordinal out of that account, as long as it's not in an active order. On the other side, let's say that the buyer deposits USDC. This user will deposit their ordinal finally, and then if they decide to list this ordinal and they have an open order, the contract will not allow them to withdraw. And this is basically just so that the buyer who kind of comes in here and buys this doesn't have to worry about something happening on the Bitcoin blockchain kind of behind their back. Only this marketplace contract can allow a withdrawal, and they will only allow a withdrawal if the order isn't open. So order is now open, no withdrawals allowed. Let's say they list it for 10 USDC. On the other side, we have a buyer who will accept this listing. They say, cool, 10 USDC works for me for this ordinal. So here's where something really cool happens. So what we said before is that this seller was the only one who could request the withdrawal for the ordinal. So because this trade has now been executed, what will happen within one block, so atomically, is that the buyer will now be the only one who can request to withdraw this ordinal. So they effectively now control this ordinal. They can withdraw it to an account they control and exchange whatever they want to do. Then on the other side, the seller now is in control of that USDC. They can also withdraw it from the contract, go do what they want with it. And now we have this completed atomic transaction. So this pattern talks about an asset on Near and an asset on Bitcoin. But again, this can be generalized to any asset on any chain. In that case, basically what will happen is the marketplace contract will only be doing one thing. It'll essentially allow, it'll just be verifying that two users have agreed to swap their accounts. That's all it'll do. And like two things, it'll like let users basically list their account for sale, and that account can basically be controlling assets on any chain. And then when both users, like the seller of the account and the buyer, basically have co-signed essentially an order, then it'll decide, okay, cool, now we can basically swap control of these accounts. So it'll actually be completely agnostic to what assets are being listed on what chain. And that flexibility is what allows this contract to then support any asset on any chain, which we think is pretty exciting. So we just launched the docs for this protocol. We have a stable testnet that is up that you can try out today. So if you check out the QR code on the left, you can see those developer docs and try those examples. Mainnet coming soon. And then on the right side, you can join the developer Telegram chat, where we have all the devs who are building this and a lot of project people building different projects. And we can answer any questions that you might have or brainstorm on ideas or whatever it is that might help you on your way. And that is it. Excited to see what everyone can build with this technology. And yeah, happy to chat with anyone after this who's interested in programmable MPC or has any questions. Thanks, everyone.
All right, everyone, we're going to have a nice little 5-minute break, and then next we will be hearing about ERC20, the Open Cross-Chain Token Standard, from Eddie Yee, who is at Connext. So stay in your seats, and we'll keep rocking. I'm just going to go over here. All right, everyone, we're going to go ahead and get started with our next talk. We're going to hear from Eddie Yee, who leads integrations over at Connext. So, Eddie, take it away.
All right. Thank you. Thank you. Just going to wait for the slides to pop up. Thank you. Hey, everybody. My name is Eddie. I'm really excited to be here today to talk to you about a new ERC on the scene that I think has the potential to solve a lot of the bridging pains that we face today. We haven't shied away from bridging at all, even after all the exploits and hacks and whatnot, because realistically at this point, it's kind of like a basic need in the ecosystem. We need a way to transfer value between all of these different ecosystems and for them to be interoperable with each other. And that's where bridging comes in. But bridging comes with its own set of challenges. So let's just consider some of these challenges and where they come from. When you bridge a token, you're all aware that you're not actually moving the token from chain to chain. You're giving up your token on the original chain in order to get some representation of a token on another chain. That representation token is a claim on the original token. And bridges facilitate this process of like the give and take. And as a token issuer or a chain that wants to bring other tokens into your ecosystem, the first thing you have to do is decide, like, how do I bridge this token to a chain where it doesn't exist yet? And there are a couple of options. So you could just build your own bridge. If you choose to do that, you're going to be immediately responsible for bridge security. And that is notoriously difficult. So most people, most projects are not going to do that. Not really a viable option. If you are going to a rollup like Optimism or Arbitrum, there's actually already a canonical chain that exists there. And it just so happens that that chain underpins the entire security of the system. So it is actually the safest bridge. That makes it very common and reasonable for tokens to be bridged through canonical bridges. However, canonical bridges don't exist on every chain, only on those rollups. So if you're a token issuer and you want to go to all these hot new chains that are out there, you need to figure out something else if you want to go to those other chains. And in EVM land, the canonical bridges only connect the chain to Ethereum. So if you want to go from Optimism to Arbitrum, say, you would have to bridge from Optimism back to Ethereum, suffer the 7-day withdrawal period, and then bridge it to Arbitrum. And those two hops are relatively expensive because canonical bridges are expensive. So canonical bridges offer this secure option, but you still have to figure out other alternatives for other bridges. So historically, token issuers and projects have basically chosen one of two practical cross-chain strategies. The first one being just use multiple bridges, right? So you can use the canonical bridges, you can use a variety of third-party bridges, all the bridges. And in theory, that should allow you to get your token to all the chains that are out there. And usually, the canonical bridge version becomes what we call this like adopted version of the token, because every time a bridge deploys a different representation of your token to a different chain, you end up with like millions of these different tokens that all represent the same thing on the origin chain, but are different tokens themselves. So what you really want is you want there to be one widely adopted version that everybody uses, that all your tokens, all your users hold, all the DEXs list, and all the dApps support. So you as a project can either accept that the canonical bridged version usually becomes the adopted version because everybody in the ecosystem considers it the most safe. And so that just like naturally converges usage into that canonical version. Or on other chains where there is no canonical version, you can try to endorse one of the bridged versions and try to get everybody to use that version because it's just more convenient when dApps don't have to list like 14 different versions of the same token and everybody's kind of communicating with the same version of that token. The problem with this is that users who bridge through other bridges that don't mint that endorsed version, they have to get the version that everyone else is using at some point. So that introduces liquidity pools into this conversation. And liquidity pools introduce slippage. So now all other bridges, as part of this like last mile delivery step for you to deliver your users the actual version of the token that they want to use on that chain, there has to be a swap involved between the bridge minted version and that adopted version of the token that everyone else is using. Obviously, that makes cross-chain transfers incur slippage oftentimes. And aside from slippage being an additional cost to the user, it actually breaks composability in many cases where you need to know exactly how many tokens you're getting on the destination chain. It's not deterministic when you have slippage in the equation. Furthermore, this model means that because you have pools, you now have to source like a bunch of liquidity to minimize on slippage. And if you're a small project, you're not going to shove enough bridge volume through your token to actually generate enough revenues to incentivize LPs to create these deep pools. So you're just simply going to have a difficult time bootstrapping liquidity. If you're a larger project sitting on stacks of VC capital, like, yeah, you can just throw money and add incentives, and that makes that problem a little easier, but it's a terribly inefficient way to use capital, and it simply does not scale when you think of like what happens in the 1,000 roll-up future with 1,000 different assets on 1,000 different chains. Even that, like throwing money at it, doesn't solve it. So there's one other major issue with this model, and it's that when bridges lock tokens on the original chain, or the home chain as we sometimes refer to it, this home chain is where the original token is deployed. And every time bridges lock that token and mint a different representation on a different chain, it actually fragments that liquidity on that home chain, because each bridge contract is now custodying a slice of the total canonical collateral on the home chain. So if you want to move like a relatively large amount of tokens back to the home chain through one specific bridge, it's totally possible that that bridge doesn't actually have the canonical assets, the locked collateral on the home chain to unlock for you, which kind of breaks that guarantee of like your tokens are claims that you can claim on the origin chain at any time. So this model with multiple bridges, it introduces slippage, which is an issue, and it really makes things kind of complicated. But it allows you to get to most all the chains out there. The other option is much simpler. It's basically just vendor lock-in. So as a project, you choose one third-party bridge. You designate them as like your endorsed bridge, and the minted version of their token becomes the adopted version. You consider that version as the only like legit one on every chain that they support, and it makes things easier because that bridge now, there's only one representation, and that bridge owns all of them on every chain. So if you need to go from L2 to L2, the bridge can just burn and mint those tokens directly. No need for pools, no need for liquidity. And yeah, that sounds great because there's no slippage. But you're also only able to go to the chains that that bridge supports. But more importantly, you are now tied to, your entire token is tied to the security model of that one third-party bridge. And that introduces systemic risk. You don't, like, a classic case study is multi-chain, where projects knew of the risks of a third-party validated bridge, but they had no better alternatives on many other chains that they wanted to go to. So they had their tokens minted through multi-chain, tied themselves to the any asset system, and when things fell apart, their token is now unbacked, and they don't have control over the token. They don't have any recourse. It's done. So you're locking yourself into this proprietary token standard that introduces the systemic risk of the bridge itself, and you are not able to kind of go back from that system. It's very difficult to escape from the walled garden of a proprietary token standard minted by a single bridge, especially if you give it unbounded like minting privileges and unbounded flows through their bridge. So obviously this option is not too hot either. So just as a summary, we have bridges that mint representation tokens on other chains. they're actually free to do that. Like, it's a permissionless model. Any bridge can lock your tokens and deploy a representation and then mint your users that representation. And many projects opt for this model where they say, okay, I'm going to accept all these bridge providers. I'm going to allow all these different pathways for my tokens to be bridged. But then it necessitates a single, like, adopted version of that token to be used. Otherwise, it's just like fragmented across all these different versions, and nobody knows like what version is the real one to use. So usually you want to go through some kind of like social consensus or project endorsement to designate one version as the one that everyone should use. That introduces the need for pools, introduces slippage, and all the complexities around like having to source liquidity in order to make the UX not completely suck. The other option is that projects have endorsed just one version, just one third-party bridge. Makes things a little easier, but you introduce catastrophic risk. So those are the two main options that have been out there, and projects haven't really had a better alternative until now. Like historically, token bridging has been kind of dicey, and the incentives built on these systems are kind of skewed, right? Like, bridge providers right now are incentivized to capture as much market share as they possibly can by funneling liquidity into inefficient places or forcing projects to lock into their proprietary standards, which makes the project have to shoulder all of that risk burden. And we just think that these two options are not great, especially when we're looking forward to a 1,000 rollup future and considering bridging as like a basic primitive in this space that needs to exist. So with that context set, I can finally talk about ERC 7281. This is colloquially known as XERC20 because it's a very, very simple extension on top of the existing ERC20. And you'll see what I mean by that. But first, the design goals for this token standard, this open token standard, is to allow tokens received by users from bridges to always be the canonical version. So everyone is always receiving the useful version of the asset, and they don't have to think about like what version is everyone else using, why doesn't this dApp support like AUSDC or XUSDC or whatever. And these tokens should be bridge agnostic, meaning that any bridge that does mint and burn should be able to mint and burn these tokens. It does not make it so that, it makes it so that it's open in the sense that any bridge can actually adopt this standard. And furthermore, token issuers should be able to control the token. Like, when you have a bridge minted token, the bridge deploys that token and they maintain ownership over it. But the token issuers are the ones who actually should control that token. Bridges should not need liquidity, right? Like slippage and liquidity sourcing, all this is just additional headaches around making bridge UX like acceptable, and that's a huge problem that we think that should just not exist. Cross-chain token interactions should be slippage-free, that's self-explanatory. And then lastly, token issuers should be able to apply their own risk models to each bridge on a per bridge, per chain basis, and basically set rate limits. So that way you don't have these unbounded flows, and you always know at a cap, like in the worst case scenario, this is how much you can lose because you've set those rate limits and you've done your DD to decide how much you want to allow bridges to mint and burn. That is quite a few design goals, and you might think that it actually would require some complex additions to make like an ERC compatible with all these design goals. But actually, it's just like two things. You just add mint and burn, which already exists in a bunch of extensions, and you add the ability for owner to set rate limits. That's it. This is the entire additional interface that XERC20 introduces to ERC20. Most of these are just getter functions, and there are a couple important ones like mint burn, set rate limits. If you're a new token, all you have to do is deploy this standard, like this standard of an ERC20 with these interfaces, and you basically get all the benefits of those design goals that we had earlier. If you have an existing token, the standard introduces this concept of a lockbox contract, which is essentially just like the wrapped ETH contract. You deposit an existing token, it wraps it, and it gives you a different version of it. So you remember how I said different bridges like they lock the liquidity on the original token into their own bridge contracts. We really don't want that. We want there to be a shared resource for all bridges to be able to pull from if they need to unlock funds. So that way you don't run into like those bottleneck issues and you don't have the custody of your actual tokens living on the bridges themselves. So this lockbox contract is a shared resource across all XERC20 bridges that bridge this specific token. And what happens is you basically wrap your existing token through the lockbox. It gives you a XERC20 compatible version of the token instead, and that's the version that bridges actually mint and burn. Part of this includes like a migration path for existing tokens, right? This is how existing tokens are compatible with the standard. So over time, through project endorsement or other social consensus, you can push for people to start using the XERC20 version, and eventually liquidity will consolidate into this lockbox. This is sort of the ideal end state where everyone starts using the XERC20 version. It's completely fungible across all different bridges, and what this looks like to users is that they're just sending a cross-chain enabled token that is slippage free. And that is the simple migration path for existing tokens. So what this standard enables is an actual pathway to a 1,000 roll-up world with 1 million different assets without like having to go through liquidity hurdles or subjecting yourself to catastrophic like risk vectors of locking yourself into single bridge providers. It is actually compatible with canonical bridge maximalism. Like you can have canonical bridges mint these tokens. All you have to do is set rate limits for them, just like you would for any other bridge. And in most cases, people will probably set like higher rate limits for the canonical bridges because they're safer, and that is totally fine to do that. It also, because of the slippage-free aspect, enables like real chain abstraction use cases and allows for intent systems to give you optimal pricing without having to consider slippage. That is it. If you are a token project and you want to migrate or you want to adopt this standard, which I highly recommend, there are a bunch of resources on xerc20.com. There's a link to the official ERC that's going through the EIP process. There's a link to a reference implementation of the token built by the DeFi Wonderland team. And there's also a link to a Telegram group where a bunch of XERC20 builders have congregated to discuss the standard, improve on its implementations, and is generally a useful place for Q&A. So shout out to the people in that group right now who are really helping us build toward this like better cross-chain future. And for the rest of you who are listening, I will see you there.
Okay, everyone, we're going to have a quick 5-minute break, and then we're going to hear from Brett Lee at Obel Labs about solo staking in 2024. Hello, I am really pleased to introduce Brett Lee, who is the Chief Growth Officer at Obel Labs. He previously worked at Consensus and has been leading growth and marketing teams for over 14 years. So I'm excited to hear what you have to share with us.
Thank you so much. Hi, everyone. Really happy to be here. Excited to share today and hopefully give you guys some alpha for opportunities to solo stake. Just out of curiosity, quick show of hands, how many of you have either run a node or solo staked before? Decent amount. Okay, not too bad, not too bad. So where I wanted to start is to talk about why solo staking is so important to the Ethereum ecosystem. In many ways, solo staking is the heartbeat of Ethereum. And if you go on the Ethereum Foundation website today, you'll see that they say solo staking is the best staking option for securing Ethereum. And in many ways, this is true. It contributes to decentralization, to resiliency of the network. And while the professional validators play an important role in this space to give more opportunities for people to stake, I think everybody would agree that solo staking is still vital to the long-term health of the Ethereum network. With that said, today, solo staking is still a really small fraction of the overall stake being secured by the network today. There's estimations of anywhere between 1% and 6% of stake is being run by solo stakers, with the rest being delegated to liquid staking, to centralized exchanges, to staking pools. And so you must wonder why. If solo staking is so important to the Ethereum ecosystem, why there isn't a higher percentage of solo stakers? Well, that's because there's actually a lot of challenges to solo staking today. First, we're in the midst of what I would dare say the next bull market. I think we're all quite excited about what's going on this week. But the downside of this is that you now require more than 100K. I think the accurate count is 115K USD in order to run a validator. That's the equivalent price of 32 ETH, which is the bonding requirement. And that's not a very accessible financial amount for many people in the world. Second, it's actually pretty hard. You need to be able to run command lines. You need to have some DevOps experience. You need to know how to provision a machine that is sizable enough to be able to handle a node. So there's a lot of barriers to getting people started to begin with. And then it's even harder to do well. As you're validating, keeping your nodes up is not always easy. Troubleshooting issues that arise, not always easy. And so for many, it's just much easier to go ahead and delegate your stake to a professional validator to be run. So how do we address these challenges with solo staking today? And what I'd like to introduce to you guys today is a new term. Well, I guess it's not really that new anymore, but this idea of squad staking. This term originated from Anthony Sassano and in a conversation with the Bankless team about a year ago, it was last April. And Anthony Sassano was participating in Obel's early alpha mainnet launch, running a DV cluster on mainnet. And he introduced distributed validators as this idea of squad staking, essentially running a node with a group of people together. So what does that mean? So let me first introduce you to distributed validators, which is the technology that enables squad staking. It's actually pretty easy to understand. It's essentially the concept of taking a single validator and running it across multiple machines, where each machine is running a partial key share. And you have to have at least 66% of the nodes up and running in order for that validator to be online. But with that simple concept, there's actually a lot of benefits, and it provides a ton of opportunities for solo stakers. What are those? First, well, it reduces the ETH requirement for each operator. You can imagine that I no longer myself need the full 32 ETH bond. I can have 4 people with 8 ETH each, have 7 people with whatever that math is, less ETH each, and 10 people with 3.2 ETH each, all pulling that together and running a validator. Secondly, it greatly increases the fault tolerance of the validator. So as I mentioned, you only need 66% of those nodes to be up and running in order for that validator to be up and running, which is very different from what it is today, where a single validator is a single machine or a single node. If that machine is down, that entire validator is offline. And so it's much easier now for solo stakers to maintain really high quality validators because you have that inherent fault tolerance built directly into the validator itself. Third, there's a natural team camaraderie to this. You're now sharing with a group of 3 others, 6 others, 9 others, the responsibility of running a validator. You can support each other, you can learn from each other, you can have expert validators now running with more new or novice validators, all for the good of having more solo stakers in the Ethereum network. And finally, I think it's really important to understand that this also greatly reduces Byzantine risk. So what is that? Well, today, every validator has a full private key. If that is a bad actor, or if I want to trust my stake with somebody else and they have my full validator private key, what's preventing them from taking that private key and running away with my ETH? There's not that much protection. And so with squat staking now, no individual in that cluster ever has the full private key. And so it's much easier for a third party to trust their stake with a community cluster because you increase that Byzantine fault tolerance. And what this has introduced is this idea of home staking. So what is that? It's essentially you as a solo, what previously was a solo staker, being able to run a validator in your home, but have third-party ETH flowing into you because there's increased trust properties to that community cluster. And this opens up a ton of opportunities for solo stakers because you no longer have to have, in some cases, any ETH to start to run validators for the Ethereum network. So what that translates to now are opportunities in this year for solo and home stakers to be able to participate in securing the consensus layer of the Ethereum network. And I'd like to share some of those opportunities to give you a little bit of alpha as to what those are. First, we're seeing a lot of organically created community squat staking clusters in the world today. So currently at Obel, we're in our mainnet open beta release, which means anybody can go ahead and run a cluster, a DV cluster with Obel, up to 1 validator. And in some cases, we can increase that limit. So what that has led to is organically created community clusters, some started by SuperFizz, now starting to see others, basically organize themselves through Twitter, through other means, getting a group of 10 people together and starting their own cluster, pooling their ETH, and starting to run a community validator. There's a lot of now KOLs, influencers, height net worth, and other individuals in the community starting to take interest in running squat staking clusters. Second, we're also starting to see this permeate to Web3 core teams. Though there's a lot of development and exciting new innovations happening in Ethereum and the Ethereum network today, not many people are actually participating in securing the base layer of Ethereum, which is the consensus layer. And so recently, Aragon, they actually reached out to us to start this idea of team staking, which is getting more Web3 core teams to squat stake within their teams. And not only are they participating now in securing the network, they're learning some of the foundations of what makes the Ethereum network strong and adding and contributing to the overall ethos of the network. So if there's any Web3 core teams here, this is a call out that if you're interested in team staking, please reach out to us and we'll be able to help you. Third, as I mentioned with home staking, there are now more and more liquid staking protocols looking to decentralize their node operator set. And because of the Byzantine properties now of DVT, they can trust community clusters with allocation of their stake. The first example of this is EtherFi. And we launched Operation Solo Staker actually about 6 months ago, if not more. And it's essentially the opportunity for solo stakers to become node operators for the EtherFi network. Currently, this program has solo stakers in 35 countries across 6 different continents. And we actually had the first distributed validator set up using Starlink in Kenya. And so some of the fault tolerance properties of squat staking is enabling people to start staking from and running validators from parts of the world that never used to have this opportunity because of poor internet, because of the cost of a machine, et cetera. And there's no bonding requirements here because of the, again, increased fault tolerance of Byzantine properties. As long as you are experienced in running a node, you can join EtherFi as a node operator without any bond today. Second, last but not least, is Lido Simple DBT. So for those of you that are familiar with Lido, Lido recently launched their V2, where they're introducing new modules with different setups for operators. The first additional module in Lido V2 that's going on mainnet here in a few weeks is called Simple DBT, which is a community-oriented module where there's smaller solo stakers, home stakers, participating in as a node operator for the Lido network. This was approved by the Lido DAO to proceed to mainnet, and this will introduce 139 new operators to Lido, which about 4x's their existing operator set. This is the first time that community validators are being added to the Lido network. We're going to start with about 0.5% of stake, of overall Lido stake, and grow to 2% and more over time. So this is also open to any solo/community validators that have experience running validators or running distributed validators today. Again, there is no bond requirement to this, and we are actively, together with Lido, looking for participants in the next phase of the testnet, which would then qualify you to go to mainnet in future phases. So these four examples are all exciting opportunities for any solo staker who wants to start running validators, an opportunity to do so, whether you have ETH and you want to stake your own ETH, or whether you don't have any ETH that you would want to stake yourself, but you want to earn opportunities for these liquid staking protocols to be able to run node operators for. So the last question I think some of you may be asking, those of you that are already experienced as well, this also applies to you, by the way, is how do I get started? You know, if I want to earn these opportunities, if I don't feel experienced or comfortable enough running a validator myself, how do I actually get started? What we've introduced is the Obel Technique credential. And this is solving a really important gap in the market today, where solo stakers, it's very difficult to showcase or to prove their experience. You basically have to take them at their word. And so for many liquid staking protocols and those looking to allocate stake to community clusters or solo stakers, it's hard to trust solo stakers today. And so this Technique credential is actually something we've introduced to try to bridge that gap. So what is it? First, it's an opportunity to learn and gain experience running DBs. There is a large community that we've run and support structure in place to educate people who are interested in running validators and running distributed validators to start to do that. Second, once you are able to run a distributed validator, you will earn a soulbound token that proves your experience running a DB. And so that is an attestation that you have this experience, and that is on-chain and provable. In order to earn this credential, you also have to hit certain requirements around uptime, effectiveness, et cetera, that not only shows that you can run a DB, but you can run a validator well. And what are we going to do with this? Well, this is being socialized with Lido, with EtherFi, with other liquid staking protocols that are looking for community node operators. And this is a way for you to prove that you have experience running a high-quality validator that would earn you opportunities into these various community staking modules. Finally, this is an opportunity for you to join the over 34,000 people within our Obel community and basically start to learn and network with other operators in this space. And we are putting a lot of support and resources into making this credential successful and something that becomes recognized in the industry to provide more opportunities for solo stakers to start running validators on mainnet. So just to close off, this is a call to action for all of you. I think squad staking is an opportunity now for everybody. Those that want to, are thinking about, are interested in running your own nodes to be able to start doing so. And in turn, what you are doing is helping to decentralize the overall Ethereum network, to make it more resilient, and to further the ethos of Ethereum. And so I encourage everybody to start looking into this. And if you have any questions, happy to answer them afterwards. Thank you all.
Hello, friends. We are going to take a break until 1:20 when we will be hearing from a panel speaking on restaking in the modular endgame. This is going to be a stacked panel. There's been some good preparation, so stick around. Hello, everyone. Thank you for joining us. We are going to get started on this next panel that we have in store for you, Restaking in the Modular Endgame. On our panel today, I'd like to welcome Sean O'Connor. Sean is Chief of Staff at BlockNative, where he is working to improve the observability of public blockchain networks. Next to Sean, we have Talita Franklin, who is a network lead and part of the research team at Chorus One with a BS in computer science and MBA in capital markets and derivatives. Next, I'd like to introduce Stanley He. Stanley is the co-founder of Linear Protocol, the biggest liquid staking protocol on Near. Finally, we will also have Tina Haibodi joining us, probably just maybe running in on stage while the panel has already begun. She leads strategy and product over at EigenLayer, and in the past, she was leading product at Fuel Network. Enjoy.
Awesome. Thanks so much for having us. We're really excited to dig in today. Want to start off today and ask our panelists to first, can you just define what the modular endgame means in the context of restaking?
Sure. What the modular endgame is in the context of restaking. Can you start?
Yeah, sure. I mean, like, modularity generally means you separate different parts in blockchain and making them like individual components, and which can be like combined freely. Like basically, like in a blockchain system, you have settlement, you have execution, you have data availability. And in the beginning, those three are like all bonded together within a single blockchain. Like Ethereum, like in the previously on Ethereum, you settle on Ethereum and the execution client execute everything, and also all transactional data are posted on Ethereum. So that's what we call a monolithic blockchain. And today, most blockchains are still monolithic. But we are right now, I'll say, entering a modular stage where we are kind of separating those parts. We have chains like Celestia, who's specializing in data availability, and we have Ethereum, who's trying to become a settlement like hub, for everything. And also we have, specialized like execution layers, like layer twos, who's only like executing transactions but posting data on DA layers and settling on Ethereum or other chains. So like with restaking, I'll say everything will be like more unified on the restaking. So it feels like we are like breaking chains up with modularity, but we are like kind of combining them together again with restaking, because restaking basically allows you to reuse security provided by a chain. So with so like in the context of modularity, like today you can basically use Ethereum to secure a DA layer that's not Ethereum with restaking, and you can use Ethereum again to like secure another layer that's not Ethereum but in the modular system. So yeah, I think that's my definition. Yeah.
Thank you.
Yeah, I'd say that to complement with that is that on the end game of modularity would be where the incentives are aligned for all the players in the chain, let's say. So for example, for node operators who has the overhead on the operational side, and for stakers who are engaging with more complexity and that can bring more risk to their strategies. So the economic part and also the interoperability, because the modularity requires you tend to have much more fragmentation of liquidity. So it would be ideal that not only restaking is implemented, but also a way in which you can move this liquidity across all these applications running on top of the same ecosystem.
Yeah, I mean, the Ethereum roadmap is so focused on modularity going forward, and I see restaking is going to only exponentially increase our ability to get there, because you don't have to bootstrap liquidity for your protocol from day one. You can outsource a lot of that economic security to the second largest base layer out there after Bitcoin. As we're looking to get into it, I really want to dig into your perspective as a validator. What are some of the challenges that you foresee for the validator ecosystem as we look to adopt restaking?
I think for what we have seen is that the node operators are getting adapt to the increase in operational work and also responsibilities in general, because you have we need to implement form of governance that you can represent your users, the people staking with you. For example, when you choose which AVSs you're gonna onboard, and it requires a lot of research to make sure that you are not engaging with projects that will only increase the risk and not really reflect on good APIs, for example, for your users. So you can also have regulatory concerns in which you can do that without being classified as an asset manager, for example. So we have seen a lot of these discussions, but it's a living thing, and most of them don't really have a clear answer right now.
Yeah, no, there's a lot of regulatory ambiguity, and I think we're going to have to pathfind our way through this. Stanley, anything you want to add there?
No, I think that's pretty comprehensive. Like as a liquid staking provider, like we work very closely with with node operators and like staking, I would say solutions. And for us, it's like restaking actually changed the whole staking business. Either staking or liquid staking. Yeah, because previously everyone's just securing a single chain and just collecting that base APY. Just very little room, at least on the yield side, for different solutions to actually differentiate. But right now, with restaking, I think we're actually transforming the staking service into a, like at least from the LST side, it's like a liquid wrapper of a general purpose security provider. Like, a node operator can operate so many things, but still under the umbrella of, let's say, Ethereum. So I think that's, what makes things so much more fun, but also so much more complex. Yeah.
Yeah, Stanley, I want to double click on something you said there. As a liquid staking provider, what are the implications or the differences between native restaking and liquid restaking, and how are you thinking about that?
Yeah, so that's a good question. I think like probably Tina will have a better answer.
Yeah.
But from what I know, so like native restaking is the most, I would say, canonical way of restaking. So like basically a Ethereum node opt-in, as a and basically restake that 32 ETH in a node to EigenLayer. So I think and that kind of like binds the security of that node to whatever restaking service the node is providing. So I think like that, and I think that's also why people were discussing whether restaking will overload consensus, because there can be like a cascade slashing. If a node gets slashed in an AVS, probably it's also gonna get slashed on Ethereum, which will make Ethereum network less stable. And I think that for AVS, for applications who want to achieve ultimate decentralization, they will want to choose native restaking. They probably will only allow native restakers to secure their network. And with like liquid restaking or like restaking with LST, let's say SEs or REs, you deposit them on EigenLayer directly. That's like kind of I don't know, like there isn't much thing can be done on the LST side. So like it's purely user activity. I think they obviously it feels more centralized, and it's not that closely binded with Ethereum-based security. So that actually could be a kind of in some way a better solution for many applications who don't want to mess up Ethereum. Yeah, and from our perspective, we actually want to support both. So like right now we are bringing out layer 1 assets to EigenLayer, basically allowing EigenLayer AVS to use not only Ethereum but BTC, Solana, Near, Atom for security. And we're gonna allow for ultimate flexibility, which means you can do vanilla like liquid risk-taking, just use our like the most fundamental LSTs, but also we will like offer risk-tranched products, basically and to users who like prefer a higher like risk profile. So yeah.
Very cool. Anything you want to add to that?
Yes, I think if you think a little bit more on the technical side, that's where on the operational, on the node operator perspective, we are more concerned about, is that the native staking, it's something that is implemented on the protocol level. So the protocol recognizes what exactly is going on there. And when you go to restaking and liquid restaking, you are adding complexity to the protocol layer, which is not really recognized by the protocol. And so you are actually engaging with an application that has a direct impact on the consensus layer and in the layer around protocol and security. So not only developers, but node operators and users need to keep that in mind. And I think this is also something that we'll be watching as it develops. I think it's not really obvious the real dynamic of applications impacting the protocol layer.
Yeah,
I mean, it's
yeah.
a bit abstract, but this is how I tend to think about the differences.
To steal an old phrase, there's no free lunch, and that extra yield is coming from increased risk. So where do you see this changing the governance landscape for both Ethereum and applications that decide to outsource their security to restaking protocols?
I'd say governance will play a very relevant role, as we have seen, for example, on the liquid staking part, that we have DAOs who tend to coordinate many things on which operators are part of the protocol, and a cap that we use, for example, for Ethereum that needs to be less than 30%, for example. I think we might tend to see similar things for restaking. What is the ideal cap for liquid staking in the protocol? Because restaking and the capital efficiency, let's say, perspective can be seen as leverage, and leverage is risk.
Yeah.
So I think governance will need to be reflected as well on, for example, as I mentioned before, how do you make sure that the applications are really reflecting the base layer users that are really staking with the node operators, because you have the node operators in the middle. So what is really how does this mechanism gonna work? There will be, you don't have really on-chain governance, for example, right now, as we have seen in Cosmos. Because Cosmos has now a liquid staking module, but this is implemented on the protocol layer, and the governance is also a chain. So it's easier to make sure that all the decisions are really reflecting the community.
Yeah. I mean, like there is no on-chain governance for Ethereum, but if you look at the reality, you have to you have to admit that the LDO token has some sort of governance power, at least on Ethereum, whatever that means, because there's no governance for Ethereum. I think like in the context of restaking, things will get more extreme, because with AVS, let's say in the future, if most of the new applications, new node networks are launched with restaking, like Ethereum layer 1 and Ethereum holders and restaking pipeline players will have a very, I'll say, a very strong say on AVS. So I think that should be the part that where the governance mechanism should be focused on. Like we have to make sure that it's not about the AVS themselves, but also about like restaking providers like EigenLayer or like LRTs, LSTs. They have to like distribute their governance power more fairly to users, and like otherwise it's not only about their own protocol, but it's about like a whole world of AVS projects. And what we don't want to see is a governance monopoly like this one token actually governing like almost everything. I mean, I'm pretty sure like a lot of people want to build this because it sounds super profitable, but we actually don't really want to, we don't really want this dystopia to happen. So I think that's where we are looking at now. We are trying to just to avoid this future, but also making sure that there's real value accrual to different layers of governance.
Yeah, and we've seen social consensus mechanisms already in play with like against Lido per se for reaching thresholds that, while not baked into the protocol, are deemed by the community to be worrisome and potentially problematic. I could see us reaching a state maybe this time next year where the community is starting to talk about what those thresholds are for different liquid staking providers and when we need to pump the brakes a little. Khaled, I was curious if are there other lessons from the Cosmos ecosystem or other liquid restaking protocols that you think Ethereum should learn from and take some best practices towards?
I'd say that restaking is also quite new in the Cosmos, although it's already implemented, as I mentioned. But the way that is implemented right now, it's called replicated security, so that there is a governance proposal in which users, stakers, and node operators vote to be onboarded as a consumer chain. And then doing the parallel to Ethereum and restaking on Ethereum, consumer chain would be an AVS. And then once this governance passes, all the validators onboard that ICS. So that's why it's called replicated security. That would be very different from what we expect to be implemented in EigenLayer, because you can actually opt in for each AVS. So I'm not sure how that would be comparable, let's say. But I think, as I mentioned before, the governance, I think, would be one of the biggest lessons to be inspired from the Cosmos, I think.
Awesome. Hey, Tina, thanks for joining us. Sorry some of your time got slashed. Just pull the mic about 2 inches from your mouth. And I'm going to throw a question over to you to jump right in. Can you give us a little bit of a sense about data availability and how restaking is going to change that ecosystem?
Yeah, so for context, I work on product and strategy at EigenLayer, and I work both with the Stakers and Operators team and EigenDA. And I used to lead product at a rollup, which was Fuel. And I think the ability to enhance rollups is like the biggest aspect that EigenLayer has for the ecosystem. A lot of people just think of restaking and EigenDA as two siloed products. But the biggest issue that I saw working it directly at a rollup and trying to bootstrap a proof of authority launch that would transition eventually to a proof of staking launch was that finding liquidity for the initial launch and then finding a validator set is very frustrating. And a lot of these rollups actually end up choosing LPs that are either within their existing investment arms or their existing investor pool, or validator firms that are also in their existing investor pools. And this is a large centralization risk. So the caveat is that EigenLayer actually bootstraps those two biggest problems, the problem of liquidity and then the problem of getting a validator set. We have 5,000 operators, last I checked. I think it's 5,388 right now. And that is the highest amount of validators in the Ethereum ecosystem outside of Ethereum itself. So that is the best way to actually have a decentralized rollup with an existing validator set and liquidity that is with ETH itself.
Yeah, I think we're on the cusp of DAs really taking off, and this restaking will enable an increasing amount of L2s to potentially shift out to DA. How do you view the DA landscape as changing over the next 24 months as restaking coming online?
Would you like to start?
No, you go ahead. I want to know your viewpoints as stakers and staker firms as well.
Well, I anticipate a lot of different chains offering DA services. And I imagine that people will be, like applications will be trying all of them, and there might be a convergence to what is the really value added by the DA layer. That we already have this, the idea of the need for it, but how many do we need, and what is really the price that applications are keen to pay for it? Because since every time you increase the price, the cost in the whole chain for an application, you reflect on a smaller API for holders. And so this is a big challenge of increasing the level of layers and intermediaries to achieve the same goal, let's say. So I think this is what I'm most curious to see the result.
Yeah, I mean, like there's currently nothing stopping you from using Google Sheet as DA, right? So yeah, I mean, like, so, and that tells us, you know, what we truly care about DA is, you know, stability, security, decentralization. So, like right now, obviously, layer 2 is using, Ethereum core data. It's probably like the safest way, as DA, because, it's as safe as Ethereum itself. And then, after 4844, it's going to be block space, still, as safe as Ethereum itself. Like right now, we see layer 2s, some layer 2s moving to Celestia, like external DA layers, because, it's simply cheaper. And some other services, they are just moving to like off-chain, that are very, committee, if they don't really care about like, a decentralized DA that much. So I think with restaking, what we will allow is a more, I hate to use this word, but a more aligned DA layer. Like, right now, like Celestia is probably like the hottest, DA layer out there, and it's, it has nothing to do with Ethereum. I mean, I think it's a good chain, but I think there could be a premium that people are willing to pay for a DA layer that's more closely connected to the settlement layer. Like, because like first, on a technical side, there's a bridging problem, right? So like validators and maybe smart contracts need to have access to that data on the DA layer when they need. And so there's this bridge problem. There's this bridging problem. And the second, I think it's purely from I don't know, from social consensus perspective. If you are using this chain as settlement, you probably also want to use a relevant sort of service for DA, and that's just my gut feeling. I mean, there's nothing again, there's nothing stopping you from using other solutions, but I think restaking actually, gives people an opportunity, to use a cheaper DA, but that's still somehow connected to, to Ethereum. So I think that premium is something people are willing to pay. That's my guess. So.
Yeah, and I also think like alignment's kind of a meme, and is actually originally used by Scroll First. So hats off to their team. But I do think that because we work closely with the Ethereum Foundation, it is a benefit. There are a lot of other benefits that include like cost and speed, and because we're not live on mainnet yet, I don't think there's a direct comparison to alternative solutions like Celestia or Avail. I think the biggest benefit for users is actually that it's similar to a cloud service provider. So it's kind of like this package deal where we're doing a lot of integrations with rollups as a service and different rollup frameworks like Optimism and Arbitrum, where we're offering kind of package services with them. And let's say like Arbitrum's antitrust, with Conduit's self-serve deployment service and Gelato's self-serve deployment service, because developers aren't going to be going on forums and trying to verify and validate which of these modular package systems or develop package systems all go together. And it's very frustrating as a developer to do that. But what they are going to do is based on, let's say, their use cases, like gaming, like DeFi, and based on the transaction volume or the trading volume that they're going to incur and the burn of ETH fees that they will foresee, they're going to select a package of services. And I think the case that you're seeing right now is like Optimism is known for a roll-up framework for these different DA solutions for particularly like NFT use cases. And Arbitrum is known for DeFi protocols. And having cloud service provider packages like that actually makes the developer product experience a lot better. And the last thing I will know actually is that really, other than that, like user experience and developer experience, developers really only care about costs. They care about nothing but cost. I was talking to like multiple DeFi founders that were doing maybe 40 to 100 ETH in burn a month, and they were going to go bankrupt if there wasn't an alternative DA solution. So some of them are onboarded to Celestia because it's the only solution that's available. So it's not because they're doing trade-offs, but it's because they need what's available right now, because there's company will go bankrupt. And when there's a more competitive market, that's better for developers as a whole. So I think all solutions are great. It's just different use cases and different benefits.
Yeah. So you heard it here first. Next year will be Google Drive DA, and we'll move on from there as an ecosystem. It's like the costs of writing to the base layer are prohibitive for a lot of individual end users. And as like I want to dig into a little bit of the title of this talk, modularity as an end game. Like, I question if that's actually the end game of Ethereum as a whole. I know we've talked a lot about it as an ecosystem, but modularity without interoperability between the different layers seems to be setting us up for a world of pain as an ecosystem. And I'm wondering, where does restaking fit into that, and how will restaking help to increase interoperability between the different modular parts of the ecosystem?
Start. Well, as I mentioned in the beginning, I think restaking might be the first step on Ethereum to adopt a more modular approach, but we definitely need to do better on the interoperability side. I know even like restaking will probably allow that with, for example, this idea that I've seen Sriran mentioning of like watchtowers and instant finality. So perhaps you can have like AVSs implementing layers of communication between all these applications, which I think is it's great. And yeah, definitely this would be, in my perspective, something that would be required for the end game. So I think restaking is just like the first step.
Yeah.
I can just add one more thing. I just thought about it. I think also part of the end game would be more MAV solutions on the AVSs, because now this is very relevant happening on the base layer. And as we might expect seeing most of the execution moving to the application layers instead of the layer one. And we have a very strong MEV model happening on Ethereum right now, but we should expect seeing this also be implemented on rollups and other AVSs. Yeah.
Yeah.
Yeah, I think Tina should probably onboard Suave as an AVS, right? I think like this monolithic versus modular debate has been going on for years. Like here, I do think modular is the future, because like blockchain is is a replicated ledger basically. So it's for trustless decentralized consensus, which means it's inherently less effective, less efficient than a centralized server. And there's no way there's no way to bypass that. So I think like the key, like the core value a chain can provide is security. It's consensus. And I think what Eigenlayer is doing is to to make the best use of consensus and security. So I think this centralized, more or less centralized execution and decentralized verification and validation, I think that's definitely the future. I think that looks like future to me. I think like obviously there can be, and I don't necessarily think like monolithic and modular, they are like they're like a one into sort of choice. So I think they probably gonna finally merge like a super powerful monolithic chain like with I don't know millions of TPS, and probably it still wanna borrow security from a more decentralized network. So I think probably they're gonna merge in the future, and and hopefully we will see restaking playing a vital role in that process.
Yeah, restaking as an enabler. Tina, any thoughts?
Yeah, so I actually think the interoperability issue, the most contentious solution right now is probably prover networks. And I think you started to mention it at the beginning when you referenced watchtower networks. And my favorite possibly is Witness Chain that works directly with us as an ABS. And as we have more ABSs that are doing actual proofs of different balances, of validations, and signing on EigenLayer's network, and restaking on EigenLayer as a whole, that might be a potential solution, but there are also trade-offs of using prover networks. And I think that's not being discussed yet. And I think it's because a lot of the co-founders and researchers that are working on prover networks or solver networks don't want to point out the security risks that are involved with a lot of people working on constricting different proof systems. And once there's a security risk or vulnerability in a proof system that's made in an attestation on one chain with another attestation, then we're going to see a lot of potential hacks or vulnerabilities come about. So this is definitely probably my favorite solution that researchers are discussing. And I love the potential of ABSs using it, but I also wanted to point out the risks. Another thing that I want to say is I think modular is just a narrative. And I think it's a great way to sell the product. And it's a very great way to make it feasible and accessible to developers and users to understand what Celestia is. But I don't believe that right now the developer experience that we're building is modular. From the way that developers currently deploy a DA layer, to the way that they deploy a rollup, to the way that they even set up a validator, there's nothing modular about it right now. It's very hard, the developer experience is poor, and modular is a narrative that we sell for having prepackaged systems and systems that they can customize this experience. And it's really great to onboard them and help them understand kind of what it means. But I think we need to think past that and then how we can improve cloud services and the developer experience as a whole.
Yeah, if we want to move the entire world on chain, we need to make it easy for developers, and we need to have high transaction throughput, which I'm excited about the potential for restaking to enable that and to help drive more shared security across the ecosystem. We're running towards the end of our time for this panel. Is there any final thoughts or closing thoughts from the panelists?
Yeah, based on the last discussion and Tina's comment, I think that perhaps the developer experience is a great example of something that we can try to borrow as well from the Cosmos. For what I have heard from the developers, from Cosmos developers, the experience is very fluid there, it seems. So yeah, perhaps there will be more for us to be inspired from the Cosmos, I would say.
Yeah. So I think the last thing I want to say is, although we are like reusing security with restaking, I think the future will still be like multi-chain. So I don't think like any one chain will monopolize security providing. And what we are trying to do right now is to actually connect those chains and to make the best use of the security that they provide. Not only Ethereum, but also BTC or NEAR or Solana. So I think that's like the end game in our head, and yeah, it's a lovely discussion.
Yeah, I would say we're only live on Goerli testnet for our operators and ABSs right now. So if you're interested in joining our rollup working group or becoming an ABS, definitely come up to me to chat or message us on Twitter. And stay tuned for our mainnet launch that is going to be very soon.
Yeah, I think it's going to be an exciting time for restaking applications, and thanks everyone for the time and great conversation. If anyone in the audience wants to catch up, the panelists will be around afterwards, and appreciate all the time. Thanks, ETH Denver.
Thank you.
Hello, hello. Cool. Hello, everyone. We are back with another presentation. This is Unlocking the Potential, the Why and How of Running Your Own Rollup by Masha Musavi. She's an integration engineer with Off-Chain Labs, and she's going to take it away.
Thank you. Is it showing? Okay, yeah, it worked. Awesome, thank you. Excited to be here. And yeah, I'll be diving into Arbitrum Orbit, and we'll learn about what is Orbit and how can you launch your L2s or L3s. So a little bit about myself. My name is Masa, and I'm an integration engineer at the Off-Chain Labs. I'm also doing PhD at Concordia University in Montreal. And this is my Twitter if you need to get in touch with me, if you have any questions about the talk, whatever. And this is my website anyways. All right, so let's dive into the Orbit and do a quick intro. So what is Orbit? So maybe most of you, or even all of you, you've heard about Arbitrum 1 or Arbitrum Nova. These are our public chains that have been live for quite a while now. They have a lot of users, they have a lot of applications, and they have been saving a lot of gas for us so far. So there's this specific piece of technology behind these two public chains that enable them to operate. And what is exciting about Arbitrum Orbit is that the Orbit program allows you to grab that specific piece of technology and then do whatever you want with it. You can even grab Arbitrum 1 and then launch it under a totally different name and branding, but the tech would be the same. So let's look at how Orbit evolved through the time. So when we first launched Orbit, the program, it was only about the L3s, permissionless ones. So it enabled everyone to launch their L3 chains on Arbitrum 1 and Arbitrum Nova. So at that point, there was no need to go through the DAO, no need to get any permission from the DAO, and it was totally permissionless. But if anyone wanted to do their L2 Orbit, they had to go through the DAO. So they need to get the license. So they would go to the DAO Foundation and they would get the license, and then they were able to launch their Orbit chain. But this caused a lot of frictions, and because there's always this general desire for efficiency, we decided to make it more efficient. So what we did is we did a lot of community calls. There was a lot of DAO talks, calls, and then we decided to come up with an Arbitrum expansion program, which is basically a program that allows everyone to launch their L2 and L3 chains, totally permissionless, no need to get any permission from the DAO, and there's no fee except for you have to pay a portion of your sequencer fees to the DAO because you need, it's kind of a revenue sharing, so you need to share your revenue with the DAO. And it's awesome because let's say you want the best L2 stack that is available in the community, you can just grab it and you don't even have to go ahead and talk about it publicly beforehand. So so this Arbitrum expansion program is what we call a community source license. So you can grab the tech, it's kind of an open source, but at the same time, you're paying back to the community by sharing the revenue with the Arbitrum DAO. So it's really cool. And so there are two types of orbit chain, L3 orbit chains and L2 orbit chains, as I said. And both of them are permissionless. Both of them, they can settle to any chain that derives its security from Ethereum. It can be Arbitrum 1, Arbitrum Nova. It can be even Base and Optimism, so any chain, basically. So this is really cool about it. And both of these chains can use either rollup or any trust technologies, which I'm going to go ahead later in the talk and discuss them further. So what is Orbit? How hard it was for us to come up with Orbit. So for Arbitrum 1, the rollup technology, in order to operate, the way it works is there are some smart contracts that they're deployed on Ethereum L1, and we have roll-up smart contracts, we have bridge smart contracts, that they are all responsible for communication between L1 and L2, and also the security of those communications. So what is Arbitrum Orbit is basically you can grab those same exact smart contracts with very minor modifications, and you can just deploy it on any parent chain. Let's say you want to do an L3 on top of Arbitrum 1, you would go ahead and deploy those smart contracts with those modifications that I mentioned on Arbitrum 1, and then you have your Orbit L3 on R1. And you, of course, you have to do some minor modifications on the node software as well to provide support for that. So was it hard to come up with Orbit? Not quite, but it wasn't really easy either. All right, so why, maybe you have this question of why would you want your Arbitrum Orbit if you have already access to Arbitrum 1 and you can go ahead and use it and interact with it? So there are tons of the reasons that it might push you to do your Orbit chain, which I'm only gonna go through some of them here, but I'm hoping that that will inspire you to think even beyond what I'm gonna describe. So the first one is you can go ahead and totally customize the software, the state transition function. So Arbitrum 1, the way it operates, it's been always in line with Ethereum. So it has this motto that it's always EVM compatible, and it was always like that. But this it doesn't have to be the case for Orbit chain at all. So what you can do is you can grab the tech behind Arbitrum 1, and based on your needs for your protocol, you can do anything basically. So I have some examples here. Hopefully they will inspire you. The first one is you can do native account abstraction and directly integrate smart contract wallets in your chain. You can add support for those EIPs that you think Ethereum is not going to add support for them anytime soon. And you can have access control in place, so you can have part of your chain or even the entire chain private and permission. And basically, the possibilities are endless, so you can do anything. So hopefully, these are inspiring enough for you. The second reason is the gas price reliability. So when you deploy an application on Arbitrum 1, Arbitrum Nova, or basically any blockchain, the cost for your user, the cost depends on what other applications exist on that chain and what is going on that chain. So block space is something that is relatively available on Arbitrum 1 now for users, but this is not going to stay the same, especially as time goes on and we have more demand. So at some point, if you have your applications on Arbitrum 1, you'd have to compete for the block space. And the way you really can hedge against that is to have your own Orbit chain. So you have a dedicated chain for your application, so your users do not have to worry about other applications monopolizing the block space. So you don't have to worry about some meme coin being launched in some specific date, which are going to monopolize the whole block space. And we have the customized protocol logic as well. So I talked about the customized state transition and the way blocks are produced, but you can totally go ahead and change the protocol logic based on your product needs. So there are some examples here that, again, I hope they will inspire you. The first one is you can incorporate different alternative data availability layers for your chain. So right now, any trust technology, it posts everything to Arbitrum Nova. So it uses Arbitrum Nova as a DA layer. And it's very strong and it's powerful, but it totally is not the only solution out there. So you can use Celestia, you can use EigenLayer or whatever DA you want, and directly incorporate that with your chain. You can develop your own governance system. So right now, our public chains, of course, they're all governed by Arbitrum DAO, but that doesn't have to be the case. So you can grab the tech and you can come up with your own governance system. You can adapt the challenge protocol to refine settlement logic. So this is the topic that has been discussed quite a while in different research forums. And you can even use innovative cross-chain communication methods. So if you've ever used Arbitrum, you know that we have this specific cross-chain communication method called retriable ticketing system. And that perfectly works, but I'm pretty sure there are tons of those methods out there that you can explore. And at the end, you can use a different sequencing model. So sequencing has been a hot topic for a while now in the rollup ecosystem. So we have decentralized, shared, and distributed sequencing. So based on your need, you can go ahead and plug in those models into your chain. Okay, so the other question that I want to address in this talk is, maybe you're thinking of why would you do an L3 instead of L2? So we'll talk about the trade-offs here, and we'll see. So the first one is the finality speed. So the way rollups achieve their finality for their transaction is through the Ethereum L1. So when you're interacting, let's say with Arbitrum 1, you send your transactions to the sequencer. The sequencer would batch those transactions, and it would post those batches back to L1, Ethereum L1. So if you really want to have the hard finality for your transactions, you have to wait for those batches to be finalized on L1. And this batch posting, it has some fixed cost that you would rather to spread over more number of transactions so that you would pay less for that. And of course, on L2, this fixed cost would be a lot less than posting on L1. So at the end of the day, the bottom line is that posting those batches on to something like Arbitrum 1 is a lot cheaper than Ethereum L1. So this way, if you have an L3 chain on top of Arbitrum 1, you can send batches more frequently in a cheaper price, and you can achieve finality a lot faster than posting to Ethereum L1. The other thing is support for Arbitrum stylus. So if you run an L3 on top of a chain that already supports stylus, you can do a lot of things. So the possibilities with stylus are endless. So stylus is a new technology that adds support for writing smart contracts, not only in Solidity, but also in C, C, and Rust. And this opens a lot of opportunities. So if you run an L3 on top of a chain that supports stylus, I wouldn't be surprised if your L3 chain is way more advanced than the current L2s. So the example is the way Outbox smart contract works on Arbitrum 1, which with Verkle trees, which has been talked about for quite a while on Ethereum. It would be more efficient, but Verkle trees, because they need some primitives that are not available on EVM, on Ethereum, they can be implemented. But on Stylus, they are feasible and possible. So they add a lot of values. And the last but not least is having the cost-effective bridging solutions. So many rollups, they rely on different bridging solutions, different exchanges, and those things that they want their users to be able to interact with. So if you have an L2 on top of L1, your users would need to go through the Ethereum blockchain. So of course, transacting on something like Ethereum is way more expensive than Arbitrum. So if you have an L3 on top of an L2, your users would need way less gas price for interacting with those exchanges and those bridging services. So things to really focus on here would be the token and ETH deposits between two chains, withdrawals, and cross-chain messaging. All right, so let's say you're sold and you want to know how you would launch your Orbit chain. So to launch your Orbit chain on mainnet, we strongly advise you to go through the rollup as a service providers, because it is a risky process and it has a lot of corner cases. Definitely, we provide support on our Discord, but this is what we recommend generally. But here, I'll walk you through how you can launch your Orbit chain on a testnet. So we provide this very simple UI tool. It's orbit.arbitrum.io. You visit that link, and you have two options. So either you can choose the rollup or any trust technologies. We're going to talk about the differences in a bit. So in a rollup orbit, in a rollup technology, the way is, for sure, I'm not going to go through the details of how rollup works, but let's say you send your transactions to the sequencer. The sequencer, as I said, it batches the transactions, compresses them, and it posts those batches to the parent chain, which in this case would be the L2 chain, let's say Arbitrum 1. So let's say you choose the Orbit rollup, and then it would open up some very basic configuration for you. You have to choose the chain ID, chain name, And then the challenge period blocks, which are the number of blocks that the dispute periods are going to take. This would be on the parent chain. And the stake token, which is a token that your validators, the chain validators need to stake in order to be able to validate the chain. This is currently hard-coded on ETH, but we will open the possibility for other ERC20 tokens as well. And base stake in Ether, the minimum amount of Ether that your validators need to stake in order to participate in a challenge protocol. And then the owner of the chain, who is the address, EOA address, that does the chain upgrades and those things. By default, it would be the wallet that deploys this chain. And you can see the gas token, which is hard-coded. You can change it. I'll tell you why. And then you have the batch poster address, which is configured automatically for you. So when you do that, when you deploy your chain on a parent chain, when the deployment transaction has gone through, this will show up, and you have to download 2 files. One of them is for configuration, the node. As I said at the beginning of the talk, you have to change the node to add support for your Orbit. And the other one is the configuration for your Orbit chain. So what you have to do is you download those 2 files, and then you would go to what we kind of like a setup script in a repo that we provide. And there are some steps that you have to go through here. There's a Docker container that you run, and it basically what it does, oh yeah, this is the setup script link that you go to after you download those files. And then there are some steps, as I said, that you have to follow. There's this Docker that you run. And once you run the Docker with those configuration files that you downloaded already, it would just launch a node with public RPC, which is reachable at your local host at this port. And also, the cool thing is that it runs a Block Scout instance for your Orbit chain. So you have everything at hand. You can use that RPC and plug it into your MetaMask and start interacting with your chain. And that is all done. So now you have, as I said, the RPC link. You have the Block Scout Explorer for your chain. And inside that output info.json file that you download, you have the chain config. You have the core contract addresses for your Orbit chain. And you have the token bridge contract addresses. So everything for your chain sitting there, you're done. So let's say you want to choose an AnyTrust. So what is the difference between AnyTrust and rollup? So remember, I just described how rollups work. So the only difference between rollup and AnyTrust is that here the sequencer would not post the batches to L1. So what it does is it posts them to a set of servers, which we call data availability servers. So those would kind of attest on those data, and they put their attestation on the parent chain, which here would be L2. So the differences between AnyTrust and rollup would be because AnyTrust does not post everything on a parent chain, it's a lot cheaper. As I said, it relies on data availability committee for those data to post to parent chain. So it's really suited for gaming and social media applications because they're not really requiring like high security because it kind of compromising security a bit for cheaper cost. And rollup specifically, they're good for financial apps which need higher security. So the only difference here for AnyTrust is that you can add your custom gas token, which is really cool. So this is not available on rollup, by the way. Only AnyTrust can have their custom gas token. So this gas token, it has to have some requirements, which I'm not going to go through because of the time limit, but we provide all the info on our docs. You can easily have whatever token that has these requirements as a custom token for your chain, which is really cool. And then there's some extra step for setting up an Orbit AnyTrust, which is to configure a key set for those data availability servers, which is really easy to follow. That the instruction is there. And then we have tools and resources available for your Orbit chains. We have an SDK for you to build these Orbit chains. We have the docs available, and we even have a monitoring tool for your Orbit chains, which is really cool. You can monitor everything about your chain. And at the end, I want to say Arbitrum is freedom. So you can basically do whatever you want with this Orbit chain. It's totally permissionless. You don't need to get any permission from DAO. And that would include my talk. I hope you really enjoyed that.
Hello, everyone. Presenting this topic is for Zircuit, challenges of building an EVM equivalent ZK rollup on the OP stack. This is Jan Gorzny. He's the technical lead for Zircuit. Here you go.
Great. Hi, thanks for the intro. Happy to be here at ETH Denver for my second talk. Maybe you will have seen something similar earlier in the week here. Maybe you've seen something similar at Dev Connect in Istanbul. Maybe this is all new. Either way, I hope you enjoy it, and I hope you see the at least slight changes that have gone on between previous iterations and this one. As mentioned, my name is Jan Gorzny. I am a tech lead and co-founder at Zircuit, and I'm here to talk to you about what we were doing without saying so much what the end result is. There will be some of that, but really some of the challenges we experienced when we were building this thing, which started off on the OP stack, which I'll talk about a little bit. Obviously, the whole talk won't be about OP or anything like that, but it is important to have a good understanding. So before I get going, I realize the more often I give this talk, the less likely this slide is necessary, but the next slide will introduce zero-knowledge rollups, and I think it's really important to understand both of the systems at the same time, because the essence of the talk is essentially we're trying to put proofs where proofs don't really belong, and that's a lot of challenges. But in order to understand where those challenges come from, you need to understand where you're putting them and what you're putting them onto. So what we're starting to put them onto as a starting point, because we didn't want to reinvent the wheel, was something called the OP stack, which is the code base that Optimism currently has for their optimistic rollup. So what is an optimistic rollup? If you've seen the last talk, you probably have a rough idea. But essentially, it's a layer 2 network where you have a sequencer. A sequencer produces some blocks. It does some stuff that gets us a nice state output, proposes a state, submits it to the layer 1. And if no one says, hey, that's a bad state route, everyone sort of says, yep, that's a good state route, and let's keep going. If someone does say, oh, that's a bad state route, then there are people in the system who are, at least in principle, can come and say, don't use that state route. That's not valid. Here's some evidence or fraud proof that suggests actually that's not a very good state route. And some things will happen, there'll be some reorgs or reversions out of that. And essentially at the end of the day, you'll get a nice consistent state. So essentially, there's this long period of time that says, challenge or not challenge a state route. And otherwise, if no one challenges, we're all good. And that's nice. It's a very nice system. It's got a good design. The little downside, though, is you got to wait this long period of time. And so we were looking at this and we thought, well, maybe we can do better for sure. Certainly, we're not the only ones to think of this. But what happens if we wanted to take this challenger and this fraud-proof system out of this otherwise pretty decent piece of software and put in a zero-knowledge proof system? Because we had heard over and over again that the OP stack is so modular and it's just ready to do all these things. And we said, well, let's try it. Let's see what will happen. And what we ended up wanting to build was something that's a zero-knowledge rollup. It's pretty straightforward. You've probably seen descriptions of these elsewhere. If not, I'll go over very quickly. But what we want to do is essentially take out that challenger from the last slide and put in this thing called a prover. So instead of generating blocks and putting a state route on chain and saying, challenge me if I'm wrong, we're going to say, here it is, and also here's a proof that says this is absolutely correct, right? And the idea is to be sure that something is correct as soon as it hits the L1. So if it's not reorged out, you actually have mathematical certainty that no one cheated you. Everything has gone right. And as a result, you don't need to wait a very long period of time. You have a much smaller finality period, whatever that means. I won't go into too many details. And you get this really nice other alternative to an optimistic rollup. And so what we wanted to do was go from this to this on the OP stack specifically. And what we really want to do is, do this without necessarily sacrificing and without reinventing all of the wheels. So what we did was we did this. It's still ongoing. It's in testnet. I'll talk to you more about that at the end. But essentially, we built this thing, and it's called Zircuit. And essentially, it's a battle-tested combination of all the best stuff that's out there, without sacrificing all the compatibility or concerns that developers would have on a zero-knowledge rollup. So in particular, we're going to use all the great tech that other people have built, customize it, make it better, improve it, do all of our cool custom tricks, but then also make sure it's a nice seamless development experience for the end developer and for the users. So we wanted to come up with something that doesn't necessarily make it easier because we've cut corners or because we've traded off the familiar tooling everyone is currently using or on board with. So the end result is Zircuit. It's a zero-knowledge rollup that is EVM compatible, and I'll tell you now about how we got to where we got, and in particular how the OP stack played a part in this. Essentially, we had been looking at the stack and some other things and doing a whole bunch of research, and we thought, there's some really cool ideas out there. There's, techniques that people are trying. There's other techniques people aren't trying. There are approaches that we wanted to try, and not necessarily, able to convince other people to try it, or we thought it was a really good idea, so we wanted to play around with it. And we were doing all this research that, why don't we just try to build one of these things? And we did. And then we sort of looked around at what the ecosystem sort of seems to be needing or wanting, maybe. And that was a little bit more of a focus on security, because we honestly believe that security can go a little bit more than just a well-engineered product, right? We can do more to protect users on the system than just be bug-free. Obviously, we do want to be bug-free, and that's something we're striving for and all of that. But maybe, especially while these systems are centralized or while they're growing, we can do more to protect the users that build on the chain. And so this is the ideas we sort of combined, and the end result is Circuit, which is starting off on the OP stack, building, not necessarily, and definitely not actually on the superchain, but still using the core infrastructure pieces. Okay, so let's go into a little bit more technical about the challenges and the sort of non-reinventing the wheel attitude that we had. We did also have a bunch of customizations, which I'll talk to you about. But like I said, there's no point in doing things that's already been done. So we took a look around and we said, okay, what is a zero-knowledge rollup? Well, we need some infrastructure, and we need some zero-knowledge proofs, and we need to be able to glue these together. And so we looked towards the optimism side of things for the infrastructure, because they had a pretty clean code base. It was pretty interesting. They were doing good development. It's all open. It's a very good license. And we get some things very, very easily, and they work reasonably well. Things like a sequencer, which you need to order transactions. Things like batchers and data availability solutions, which you need. Not necessarily the ones you need for a zero-knowledge rollup, but still something that you need to get started. In addition, you get smart contracts and the forks of Geth that you need, which are really nice. I'll talk to you about some of the struggles. But then we also needed a zero-knowledge proof system. And while I've got a PhD and I love doing this by hand, if other people have done some work, we should be inspired and take advantage of it. So we looked around, and people like PSE and others who are open source had nice implementations of particular components or particular parts, but not necessarily the whole picture, or not necessarily the whole optimized picture. So you might look at a particular set of open source circuits for a set of opcodes, and it might be pretty practical and it might work, but it might not be the best prover generation time, or it might not be, supporting the features that you want, or anything like this. And so we started on these things, but we certainly didn't finish there. And the rest of the talk is in part to convince you that actually it's not as simple as just forking two repos and saying, we're going to work together now when we're done. We have a zero-knowledge rollup. In fact, there's a ton of other work. The ton of work comes from these main areas of challenge. First, the node infrastructure that we get from Optimism is not necessarily the one that's ready for prime time. It has a lot of really cool stuff, but it also does some stuff that Optimism has decided to do for either good reasons or bad reasons, and isn't necessarily equipped for ZK prime time. So we'll talk a little bit more, but some of the high-level things are things called system transactions. If you look at an Optimism block, every block has a system transaction that updates the time of the L1, some gas prices, some other things, and injects it into the L2 block so that the L2 state can be updated. This is a pretty nice solution there, but when you're in a zero-knowledge system, that means you're now proving a bunch of transactions that are effectively just doing things to update your internal state. Can we do better? Can we do differently? The answer may be no. The answer may be yes. It's something that we're going to explore and something we're working on. Certainly, we don't necessarily have to follow their exact lead. Other things are also great and helpful. The batcher and the DA, you need that. Every rollup should be publishing data somewhere, but they're not built for zero-knowledge rollups. Your rollups might want to publish data in a way that's more ZK friendly, not the way the optimistic things do. And then we'll talk a little bit more about Geth and some smart contracts later. On the proof side, you have things that are, like I said, existing but not necessarily optimized. You have individual circuits but no way to aggregate them, so you might be able to prove them, but maybe not on the hardware you want. So you have to get in there and really change how these things are aggregated or built together or composed or otherwise engineered in order to make them work. And things like the verifier really want to be optimized so that you do it very quick. And then, of course, there's a whole bunch of other things. A sequencer and a set of ZK circuits is not a rollup. A rollup is much more than that. It's a whole functioning network, and there's a whole bunch of things that are going on behind the scenes for all of these rollups that people just generally don't talk about. You need prover pipelines, so unless you have an open place proof marketplace, you need to build that. You need front ends, you need back end support, and a bunch of things. You need documentation, and you need testing. One of the things we found was certainly testing is lacking in a lot of these areas. And then even if they're not, getting them to work on two different stacks is a real pain. So there's a whole bunch of things that you need to do to get from just what's out there to something that you can be proud of on your rollup, because you can't just glue them together and expect it to work. So we'll dive into some of those right now. And as the title says, we're going to talk about the OP stack, so I'll pick on them a bit, but honestly, it is a very good starting point, and shout out to the team. They are doing great stuff. But essentially, the main problem with the OP infrastructure, although it's open and very nice, is that it's not ready for ZK prime time. It is very good at a bunch of other things, namely optimistic rollups, but not necessarily for ZK. So there's a couple of reasons for this. I've already talked a little bit about these, this notion of system-level transactions, where you have transactions injected into every layer 2 block, which now suddenly you have to prove. If things are expensive to prove on zero-knowledge systems, you certainly don't want to be doing extra if you don't have to. So a block every 2 seconds, which is what Optimism does, with a system transaction, and every one of those can start adding up. It's not necessarily going to be the biggest cost in your system, but you start thinking, why do they do this, and can you do better? And these are the questions that this project really started to sort of question and try to answer differently. Other things, of course, are built without ZK in mind because they're not a ZK rollup. The batchers don't talk to the verifiers in terms of the data being posted and is it the right inputs to your circuit. Because if something goes wrong on an optimistic rollup, someone just gets slashed. You can point the finger and say, that guy didn't do it right, here's why, uh-oh, bad. On a zero-knowledge system, you actually need these components to talk to each other. So you need to build this engineer this component to make these systems talk to each other in a way that doesn't introduce extra trust. And other areas of change are, some of it are engineering and some of it are just different designs. But some things like the smart contracts, they're pretty good. The bridge is pretty solid. But the verifier, the logic is very embedded on the fraud-proof system or the timeouts into the bridging. Not so clean for when you're putting in a zero-knowledge proof system. And then there's other things that really sound like a really good idea on paper, like embedding Geth dependencies everywhere so that you look like Geth, you act like Geth, you look like the layer 1. That sounds really, really good. But then you look at zero-knowledge systems and you say, actually, what I really want in my Geth is not SHA-256 for hashes because that's expensive. I want to switch it to Poseidon. But only in some areas, because maybe I need to interpret L1 blocks with SHA-256, but write L2 blocks with Poseidon. And if that dependency is too tightly coupled, it's going to get very difficult. Turns out that's at least partially the case, and it's kind of a pain to disentangle that. So there's a whole bunch of things that need to change on the engineering side. Other things, again, not meant for ZK. Deposit transactions are the transactions that bring assets from L1, namely Ethereum, onto the L2. And in Optimism, if you cheat, someone points the finger, you get slashed. That's bad, but that's how the system works. Like bad in the sense that you'll go, you're not supposed to be doing that. But the system works like that, and it's totally fine. On a zero-knowledge system, you can't just invent money out of nowhere. You need to have a mathematical proof or some other way of checking with the L1 that actually this happened, because no one can point the finger and effectively take any action with you. Obviously, if someone did that, you could go on their Twitter and say, hey, don't do that. But the system would have already gotten away with the action, and there's no technical limitations unless there's a social consensus to fix it. So we have to add all of this functionality onto the Optimism stack. We have to do things like make sure that the inboxes and outboxes of deposits and corresponding withdrawals also understand that extra data needs to come from extra places and extra things need to be changed. And they have to tie all together. So this adds some work, this adds some overhead. Not necessarily, a decade's worth of work, but it's definitely non-trivial. The smart contracts, again, these are part of the systems that will need to be changed. They're some of the most important. They're pretty good, but again, not necessarily ready for ZK. They're not necessarily as modular as you want. If you look at how you do withdrawals in Optimism, it's a 2-stage withdrawal where you prove an inclusion and then you finalize it, or vice versa. And that's nice, but actually you don't need that in a ZK rollup. You can change it. Despite that, the OP stack has built it right into the sort of standard way of doing things. I can't blame them. That's what their system is going to do. But it's not necessarily what ZK people would want. Some of these points are getting a little bit less relevant. Containing legacy code, they've actually done a lot to clean up that code base. It's been very good. But there is still a lot of references to sort of V0, or at least there used to be, where a lot of the contracts are based on the initial deployment of the OP stack, which has since been migrated to newer versions. So some of this you can ignore very easily. Some of this you want to engineer out because you want your attack surface to always be as small as possible. And then again, this onboarding and offboarding is also missing. So I'm going to try to catch up with my proposed time here and go a little quicker. But beyond the OP stack, once you get all of the OP stack parts in the way that you want them and you sort of get your optimistic stack in a row, you then have to bring in zero-knowledge proofs, and this becomes challenging for another reasons. There's no one out there, as far as we know, that has a nice open source representation of things that just like automatically works out of the box with the OP stack, so you have to do things differently, right? If you're using circuits that someone built, they may not be using the same version of the Geth. There might not be opcodes that are fully supported. Optimism does a really good job of keeping up with the latest Geth updates. Other people building circuits may not necessarily be doing that. So you also have to pay a special attention to yourself to make sure that this happens and it does work. And even if you get all the opcodes you want, as I've mentioned, aggregating things, putting these pieces together, super challenging, super interesting, because you can do it in very different ways in order to A, differentiate yourself, but B, just perform better or have your requirements met. I'll pick on the system transactions one last time here. This is one of the things where the provers actually have a really hard time, because you have a system transaction that is a transaction that the system itself is trying to do to itself, just to update state in some nice way. But you don't want people paying for that because it's a system update. It's like the OP stack telling the OP stack, here's the time on L1. That's not something users should be paying for. So you say, okay, I don't charge people for that. Or I don't check a signature for that. Either it's free or I'm just going to ignore this. But how do you do that in a circuit? Well, you still have to make one of those changes or find another solution, in which case your circuits now start to look less and less like the EVM you wanted to build at the beginning, or you add more and more overhead to sort of skirt this problem. So there's actually a lot of challenges, and these might not be unique to the OP stack, and they may not be something we can totally remove in circuit, but it would be really great if we could at least explore different design spaces and maybe either reduce their frequency or do it in another unique way. Of course, as I said, sequencers and circuits do not a roll-up make. Prover pipelines don't exist, so even if you do have a nice set of circuits and you do have a nice OP stack node, getting them to talk to each other takes some time, takes some data. Provers generally need block traces, which can be fairly large, and then they need to pass this information. You need to control what blocks you're proving. If you have batch proofs, you've got to do something differently than if you don't have batch proofs, et cetera, et cetera. And things like documentation and testing also all need to be updated so they're consistent, so that at the very least you know what you're doing, but also so your developers know what you're doing. There's a whole bunch of other things we can do in this research space. Cryptographic improvements are always very valuable. We have some. We're going to keep doing some. We're going to have more. I hope that the next time I give this talk, I can give this very explicit notion of what we've actually been doing for custom stuff, but it's going to range from MSM to aggregation and everything else. And then we can also do things like security, and I'll spend the last 2 minutes talking about security. Because we believe that actually one of the really cool things about having your own rollup is to be able to add security to places where you can't otherwise add security because it's not your system. And we in particular believe that if you're running a sequencer with all these special roles anyways, especially before it's decentralized, maybe you can do some good, right? What you could do is add some level of security embedded into the sequencing protocols so that your security of your DApp users isn't just based on their smart contract ability to be non-reentrant or non-bug, don't have bugs in it. And you can involve the sequencer to do something very unique and very cool. So for example, you could have it look at transactions in the mempool, and if something's sort of bad, whatever that means, you could put it into quarantine for a little bit, and maybe it'll come back later, and maybe it won't. That's probably not for everyone, and some people might not like that, but the reality is this might save a lot of money, especially as these systems grow and evolve. So I don't know what happened with my slides there, because I didn't hit the click. I still have a minute, so I don't know what's going on here. But yeah, that's most of it. I don't see the roll. All right, you don't see this, right? Maybe it's the HDMI connection. And we're back. All right, so in the last minute, sorry guys, technical difficulties, I must have stepped on something. For the roadmap, Zircut's coming along. We've been working on it for a while. We are super stoked to have launched our mainnet our testnet at DevConnect, and we're hoping to go mainnet sometime later this year. But for now, check it out, try around, play around with it. If you have ideas for research and you want to collaborate, please let us know. If you think we've done something wrong with the OP stack and there's easier ways to do something, also let us know. Interested in all of these directions. I also would like to see what you think security on a rollup should look like, and if there's ways we can help you. So please, come check it out. Otherwise, hopefully go live when it's ready. We're not going to go too fast, break things, but we do want to go reasonably fast. Either way, if you're building a ZK rollup on the OP stack, it's not as easy as it looks. It's not just forking something and saying put a ZK system in there, but research can overcome all of these problems and can actually, at the end of the day, get you a really functional, nice rollup. And you can do some really cool stuff with it. And then you can do even more cool stuff with that. It's very unique. The result, at least the first time we've tried this, is called Circuit, and we're happy to have you part of this ecosystem. If you're interested, please reach out here, and we've got some staking things for points. Thanks.
Hello, everyone. For our next talk, it's building on Aragon-based node for Type 2 ZK EVM. And speaking with us today, who traveled 20 hours to get here, is Max Revit. He's a developer. All right, go ahead, Max.
Hey, thanks for the intro, man. So welcome. Yeah, this afternoon I want to explain to you how we modified the Ethereum implementation Aragon to build the client for Polygon CDK L2. So in the presentation, I'm going to cover the following topics. So who are Gateway FM? Like, who are we? Who's the company? I'm going to go into what is a roll-up. You've probably heard that a few times today. And what is CDK? I'm going to cover Gateway's product Presto, just in brief. And then I'm going to go into why did we choose Aragon to do this implementation. And then we're going to go through the main two parts of the system that we've built and that we're building. So the bit that we've built already is the synchronizer. So we're going to cover the EVM changes we made. We're going to cover the sparse Merkle tree. We're going to cover the dynamic fork enablement. We're going to look at the L1 and data stream sync, so where the node gets its info from. And then the bit that's work in progress, which is the sequencer. So we're going to cover virtual counters, the witness, executor verification, data stream generation, and then our load testing tool, which is the TX replayer. So who's Gateway? Gateway FM is a team of professionals in the crypto space. We build Web3 infrastructure and tooling. We have expertise in blockchain, fintech, infosec, other industries, and that lets us lend our experience to other people to sort of really help the businesses in the space. So I'm Max Revit. I'm on the R&D team. I'm a developer. My team is a group of people who've been on the Aragon team previously. So we have good experience with this node software. And we've been building solutions in the space for quite a while now. So Gateway worked with some industry leaders and some names that you will recognize, Polygon, WireX, etc. Trusted by these partners. So Presto. So Presto is Gateway's flagship product. This is rollups as a service. So 4 clicks to your own rollup. So private ZK rollups with all of the tooling. So once you've deployed that, you get KYC, block explorers, etc. So kind of, turnkey solution for a rollup. We run these rollups for other people, as well as building the technology that underpins them. So that gives us a unique perspective, and we understand the requirements for a user-friendly and performant client, and how to use this client with our Presto users. So having that R&D department also means that we produce a better product in Presto. So what is a rollup? A rollup's a layer 2 scaling solution. It will reduce costs and increase throughput by processing transactions away from the main blockchain. So when it comes to ZK rollups, there are a few types, and they each come with their own trade-offs. So a type 1 is essentially Ethereum compatible. It is basically running the L1. The issue here and the trade-off is that proofs can take a long time to generate. So realistically, that might not be the option that you want. Type 2 has minor changes. So state tree modifications, change gas costs, some small EVM changes. This comes with the benefit and the trade-off that you get quicker proofs, but you may encounter some incompatibilities when trying to run your smart contracts. We then move to the type 3, and again, the trade-off towards performance is most heavily skewed here, so it's mostly Ethereum compatible. You've got fast proofs, but you get more incompatibilities. So for example, most of them would be no pre-compiles. So CDK is a type 2 rollup, and throughout this, CDK was Hermes Polygon ZK EVM, so it's useful to know the terminology and the history, so CDK is the name we'll be using. So the question is, why did we choose to use Aragon as the node to do this? So Aragon benefits from a low footprint on disk. Anyone familiar with the node in the Ethereum L1 space will know that. It's an all-in-one solution, so RPC, transaction pool, EVM, etc. They're all there in one repo to be run. It has a stage-wise sync, so instead of going block by block, the node will sync in stages. So we can optimize some operations for the batch. So for example, in this case, we can verify multiple blocks in a single state root calculation. Aragon uses MDBX, so this has some advantages over things like Bolt and LevelDB in that it's simultaneous read whilst you're writing the DB, which means we can split the parts of the system up, and it's super fast. So as I said, you can run components of Aragon separately. A good example there being that you can separate the RPC out, and it can still talk to the database whilst it's being written and the sync is happening in the background. So it's very capable as an archival node. And it's an ideal candidate, in fact, for syncing the layer 2. So the first part of the solution that we've provided, and this is the synchronizer, this is a node that will consume and sync the blockchain, and it will allow you to then stand up an RPC. So it syncs from both the L1 and a data stream, which is produced by the sequencer. So the sequencer will produce the data stream which contains transactions, batches, and other data, and then we use L1 sequences and verifications. So the L1 verification will contain a state root, which we can use to then check and make sure that the chain is okay. So we made some adjustments to the stage sync as well. So we replaced the headers and bodies stage with a stage which actually retrieves data from this stream and pipes that into the Aragon DB, MDBX. And we have a new stage which is for creating the SMT. So we replaced the Aragon interhashes stage, and this allows us to generate a sparse Merkle tree, which will give us the state roots. So that differs a little bit from Ethereum mainnet with the Merkle tree. Where possible, we have tried to maintain upstream compatibility. So obviously this is a fork of Aragon. We want to be able to take changes from the upstream as and when they come. So we've kind of added _zkEVM to the file names and tried to, where possible, separate out the code we've written as much as we can, so that when it comes to the actual code files that are already in Aragon and in the upstream, we've made small incisions there. So hopefully when we rebase on the upstream, that's going to be a lot more easy, because we're just going to see like a function name change or something like that, and it'll be fairly clear that, okay, this is the zkEVM version, and we'll know which to take. So also we've added a new RPC namespace. So with this being an L2, there is a zkEVM namespace, and that allows you to get stuff by batch and do some operations like that around the batches. So since we're running a type 2 rollup, we had to make changes to the EVM, as discussed with the types of rollup. So this is a EVM that's based on the Berlin hard fork. We made various changes to opcodes, so Xcode hash returns the hash of contract bytecode from the state tree. Difficulties returning 0. Static call doesn't override return data, if the execution's reverted. We also have a new type of error for disabled smart contracts, so that makes it behave a bit like an error reverted. With each fork, we've changed the pre-compiles to match the CDK requirements. And we also replaced self-destruct with send all, so this prevents funds from being lost in the L2. This isn't necessarily EVM changes, but there's a couple of things that we have to write into contract storage as we do the execution. So global exit routes are placed in the global exit route manager contract storage, and then the transaction number and state route are each placed into the system contract at that point as well. So the sparse Merkle tree, this replaces the Merkle tree from the Ethereum implementation. And the benefit of sparse Merkle tree, which is a 20-minute presentation on its own, maybe longer, is that we can do efficient non-inclusion proofs. So we took an algorithm that existed from the JavaScript implementation of the node, and we made some performance increases. So as I said, we have the stage sync. Well, that means that we can do a batch-wise operation on this tree. And we added some efficiencies there so that we don't multiply hash nodes. And so we got a huge performance benefit there. We use the Aragon history so that we can incrementally update and unwind this sparse Merkle tree. And luckily we retained DB compatibility with the JS implementation, which was a huge debugging win for us because we've got a lot of state and we're trying to compare and see why our state routes have differed. So that's been a huge help as we've done the project. We've also added dynamic fork enablement. So normally in upstream Aragon, you would need to know a block height or a timestamp of which a fork would be enabled ahead of time. Here we can code for it and say that it's fork ID X. And when that fork ID is actually enabled by the chain, we'll consume that and that will set that feature set live. So this is this synchronizer is currently in alpha, and we'll be doing the beta soon. This brings me on to the sequencer. So this is a work in progress, and this is a separate mode of operation for Aragon, where the node will build blocks and batches, which will be sent to the L1. So it acts as the centralized sequencer. Now, this is obviously replacing an existing sequencer, which has a different EVM implementation. So we have virtual counters, which mimic the requirements of the CDK hardware, and they prevent us basically from overwhelming the prover. And the way we've done this is we wrap the Aragon jump table, and so different counts are assigned to different things. More expensive operations will have a higher impact here. And so we're aiming to limit work done by transactions and limit the batch data size. So because proofs are expensive, we want to maximize each batch. So as we go through, we're working with these counters. And if we hit a counter overflow, we will simply revert back to the previous transaction and then build an optimized batch size. We've implemented the witness. So the witness is a description of changes to state. So it's like a partial sparse Merkle tree. And we can send that to the prover. And we can send that to the existing executor, in fact, for reasons we'll see later. And that allows you to sort of have a stateless reconstruction. And we can use this to verify the existing sequencer implementation, which we're going to see next. So this is where we run Aragon in the sequencer mode. And obviously, once we've built a batch, we need to know that our EVM has had the same outcome as the existing executor's EVM. So we actually, we have to keep compatible with the upstream ROM. Due to performance reasons, we use a pool of executors asynchronously, and this is where the statelessness comes in with the witness, so we can verify multiple of those at once. Now, on the happy path, that's great. When there's an issue, we go into like a limbo mode that we're calling it, and so we have to sort of revert the batch to find the failing TX where there's this incompatibility, and we'll remove that transaction from the pool, and then we'll move forward again. So that's how we're dealing with the differences that we may perceive there, and obviously that will be logged, and hopefully the issues will be raised, and we can then resolve that. The sequencer does data stream generation. So at the moment, the synchronizer node we talked of is consuming the stream from the Polygon implementation of the sequencer. At this point, we will start generating that stream for these synchronizer nodes and exposing it. So pieces of the stream are being verified by the executor in that verification step as well. Obviously, whilst doing this, one of the outcomes that we want is a performant node. Performance sequencer. So we built a TX replayer, which allows us basically to push transactions into the sequencer and replay them, say, from mainnet. And that's kind of like a good real-world test. So to summarize what I've talked about, rollups are a layer 1 scaling solution. The rollup type indicates that compatibility and performance trade-off. CDK sits at the type 2, so we do get a performance benefit, but we don't introduce massive incompatibilities. Most smart contracts hopefully will work there with minimal tweaking. The reason for the project, the existing Polygon CDK ecosystem is being augmented by this Aragon-based node. I think it's going to be slightly more ergonomic for infrastructure, to run this node. And hopefully we can squeeze a little bit more performance out there as well. We've talked about the Presto ecosystem, so obviously that's gateways, rollups as a service, and we deploy things like this solution to allow you to have 4 clicks to your own private ZK rollup, which obviously is super cool and a kind of like turnkey solution. We talked about the synchronizer, which is in alpha. The beta is coming soon. And so that's for running basically your RPC nodes. And we also talked about the sequencer, which is the work in progress, where we're building blocks, batches, and submitting them to the L1. So I'd like to thank you for listening. If there are any questions, we'll be at the Polygon booth for a bit. We talked through quite a lot of deep concepts there in brief, so I'd be happy to go into a little bit more detail if anyone wants that. So yeah, thanks very much.
Hello. This is probably the most interesting title for a presentation. It's titled Before, During, and After, the Three Sides of Parallel Execution. And this is Dan O'Farron. He's an Ethereum core developer with Hyperledger Besu.
Yeah, thanks for having me here. So this particular topic about how best to bring parallelism into Ethereum in a way that benefits Ethereum more than just speed has been something I've been thinking about for a while. Here's a tweet that I did from last June. You can tell it's a real tweet for me because there's a spelling error in it. But getting just simply speed out of parallelism is a great advantage, but I think we can do much, much more about it. But we really need to change the way we think about parallelism and where we go into the execution. So we need to think about parallelism before, during, and after transaction execution. So that's the kind of the focus of this talk, to go on the three sides of it. So I'm going to talk about four things here. First, I'm going to lay down some base information about concurrency and to kind of set the foundation for where we're going to go. Then I'm going to talk about before, during, and after the transaction of how we can apply these principles to apply parallelism into Ethereum. But like true multi-threadedism, I'm going to do this out of order. I'm going to talk about concurrency, then I'm going to talk about what you can do during the transaction, and then before, and then after. So when you talk about parallelism, you go into an entire area of computer science relating to concurrency, doing multiple things at the same time, and the interactions that go with it. And it is a very broad and deep area that you could easily fill hours and hours talking about. There's stuff like Amdahl's laws, semaphores, locks, scalability, threads, context switching, transaction ordering, and all sorts of crazy things that could be impacting your concurrency. But what I'm going to be focusing on, though, is just one aspect of it, and that's about the transaction parallelism. Not even the opcode parallelism so much within a transaction, but how you can take multiple transactions and do them in parallel without interleaving them. So that's kind of the focus to kind of set the stage for what we're talking about. Now, when you talk about transactions and parallelization, you need to step back and think, well, how do they handle this in databases? And there's two common acronyms that go along with this, ACID and BASE. The SQL databases usually focus on the ACID acronym, which stands for atomic and consistent and isolated and durable. These are transactions that have a very solid meaning and a very solid reference and are very firm in what they mean. And then you get into the NoSQL camp, databases like Cassandra and all those other no databases that keep stuff moving around. You might think of data availability sampling when you think of the kind of soft things about that. And the BA stands for basic availability, soft state, and eventually consistent. Now, when it comes to a transaction and the balance in your wallet, you don't want soft state. You don't want maybe it's going to work. So you really need to focus on the ACID side of the transactions. So when we talk about parallelizing these transactions, we really need to think about the aspects that we get from the ACID characteristics. And the most important one of those is isolated. And that's something that I'll come back to when I talk about after the transaction, because that's kind of important to how we get parallelization to benefit end users. Now, the three sides of the transaction, I call it prefix, infix, and postfix parallelism, talking about whether you are doing things before the transaction, during it, or after. And the things we're going to talk about are things like UTXOs and strict access lists. Those are things you might put in your transaction before executing it. While you're executing it, you might use optimistic concurrency control, block STM, and you might do some things with opcodes called delta writes. And then afterwards, once you have that execution and you've executed it in a parallel fashion, you can use that information to create parallel receipts and to create isolated receipts and isolated proofs to where you can prove and get receipts for only what you did in that transaction without having to go through any more contortions. So let's talk about during the transaction. Let's talk about infix parallelism. Now, this is the sort of thing that is being talked about a lot and is being executed to make it simply faster because it very nicely fits into current models of the transaction. Two good examples of this are Monad and Aptos and Sui. Monad uses something called optimistic concurrency control, and Aptos and Sui created something similar but slightly different called block STM, software transactional memory. And we'll get into that in a little bit. But first, let's talk about what OCC, or optimistic concurrency control, is. When you think of parallelizing a list of tasks that you have to do, this is like the simple, obvious way of what you would do it. You would take all those tasks and you would just do them in parallel. And then afterwards, you take them together and make sure they make sense. So it's a bit more, at the high level, that's what it is. So here on the left, you'd have a bunch of transactions. You put them in a pool. and you have a bunch of parallel executors that would take those transactions out of the pool. Some transactions go quicker than other transactions. So you'll get them in a different order than necessarily that you submit them into the pool. So that's where the sort step comes in. You take these transactions and you put them back in order. Some of these transactions depend on resources that are very order dependent, and that's why you have this sorting process, because then you got to check the conflicts. If I've done things out of order and it matters and I need to do it over, you take what you executed, you throw it away, you put it back in the pool, and you bring it back through the process. But if you can verify that there's no conflicts in what you've done, then great. We've executed our transaction in parallel, we can put it in the block, and we can go on with our life. So here's kind of an example of how that might work. Let's say we have 10 transactions, and each one of the characters represents a separate resource that they use. And these resources are resources that you have to have exclusive control over, and that you have to have in the exact same order that you see them in the transaction. So if I access the club in one transaction and the club in the next transaction, I have to do it in the same order. So a simple way that you might just do the transaction parallelization is you just might say, great, let's do the odd transactions in one processor and the even transactions in another. And if everything takes about the same time, it's actually going to mostly work out, except for some cases. But these are computers, and they do strange things. And so you might give one core all the odds, the other core all the evens, and you might get them all back odds first and evens second. Even though you said do it in parallel, it might do it all in line, which isn't a problem until you get into the parts where you have a resource that you are now using out of order, that you've changed the values for. So in this case, if we do the odds first, we're going to have a problem with transaction 9 because 4 hasn't been processed yet. So the way this would work is eventually it becomes correct in OCC. So we take our initial order, we start sorting it, we go through the order, we get to transaction number 9, and we see that the star's already been used by 4, so we throw that transaction away, put it in the queue, it gets processed after 10, and then it comes back at the end, we resort it back in the same order, and we get it again. And the net effect is you've executed about 6 transactions of time to get 10 transactions, and you've nearly doubled the time, the efficiency and time-wise it takes to execute this transaction. Block STM takes a slightly different approach to this. Rather than aggregating everything at the end, while you're executing the transaction, it will look out for these conflicts. So let's say that you're executing transaction 1 and you start 7 at the same time. 7's going to see it needs the club and realizes it needs to wait for transaction number 1 to finish, so it will pause. And let's say you start number 2 and then number 8 does the same pausing routine, but let's say you're starting transaction number 3 late. Well, 8's going to be executing, it's been using the diamond, it now knows that it's useless, so it restarts and starts over with another transaction number 8. And of course, there's the same situation in OCC, where you could have completed transaction 6 before you realized you had your conflict, so you just have to pitch it out and start it over. So Block STM does about the same things that OCC does, it just does it in line and gets about the same transactions. So, as far as doing it before the transaction, you get great time improvement. Computation, if you're worried about counting CPU cycles, it could be quadratic. With user impact, well, what's great about user impact is you don't have to change a thing. It just magically works if it's done right. This parallelization, it just goes faster. And there's no impact, and there's also, beyond wall clock time, no benefit. So let's talk about taking some steps before the transaction to try and provide parallelization. And the 2 best examples that are actual live networks doing what we need are Bitcoin and Fuel VM. Now, when you think of Bitcoin, you probably don't think of parallel execution because block times are so slow. But the UTXO model is surprisingly friendly to parallel algorithms. Each transaction in Bitcoin consists of an unspent transaction output that you exclusively own and is only ever used once. So there's really not going to be any conflict. If another transaction tries and uses it, the transaction's invalid, you just pitch it and you don't even reevaluate it. So you can execute all these transactions in parallel, take all of this computational time, and you just take the outputs and you take the inputs and you have new unspent outputs. And the problem is it's not dynamic. You're locked into your inputs. There's no programmability. It's only useful as money. And oh yeah, one more thing I forgot. All these unspent transactions come from other unspent transactions. That's the important thing you should look at here. Now what Fuel does is they take this approach and they use approach that's kind of like strict access lists if you were to use it on an account-based system, but they use a UTXO-based system. And instead of locking onto a specific state, they lock onto a slot number or a resource name, some sort of an identifier of the state of the contract that is separate from the actual state held. So in your transaction, you would say, I'm going to use the spade resource and the club resource. And Fuel will find the most current UTXO from that, use it, consume it, and throw it away. So you get a lot of the same benefits for parallelized execution. Parallel is a mouthful. I really need to come up with a better word for that. But for these parallel transactions, you can execute them in parallel and consider the conflicts really easily. But the downside is when the transactions get bigger, you have to enumerate all of your dependencies up front. And what's worse is if some of your dependencies are dynamic in a function of the code, it's really going to be difficult for you to create transactions that do this effectively. So it's fragile to random things that your state contract might do. Like let's say you're calling a dynamic proxy, and by the time between when you submit the transaction and execute it, the proxy might change address. Your transaction suddenly might be invalid because you don't have enough of the resources listed in your transaction list. So when it comes to doing things before the transactions with UTXOs and strict access lists, it's kind of a mixed bag, but I think it's net negative. You do get time improvement, almost as good as OCC and block STM. But the bandwidth is kind of not so much because you got to put all of your transaction information in your transaction. And then you double down on that because you have to pre-execute all of your transactions, figure out what resources you might need, put those in the transaction and submit it. So it's more work on the user for the same sort of a benefit that you could get just from going with block STM and OCC. And you get basically the same parallelized return by doing stuff with dynamically generated conflict lists. So before, it doesn't really quite work as well as the during. And I think that's something that Monad's done some research on. And they can actually back up with stats that strict access lists are actually a net negative. So where does that leave us? That leaves us to the third side of parallel transactions. And that is, what can we do after the transaction? So we've executed in parallel, nirvana, wonderful things have happened. So what? So just to warn you, this is total blue sky zone. There's no implementations from what I'm about to describe. This is hypothetical, this is aspirational, but I think is truly what is needed to bring the benefits of parallelization into Ethereum and make end users benefit from this. So these are to create things called isolated receipts and isolated proofs by doing some changes in the process that not only make parallelization easier, but make it more useful on the back end. So to do those, I would propose two separate changes. The first one is to introduce a couple of new opcodes, peer to SLoad and SStore. We'll call it SCredit and SDebit, where as an atomic transaction, it takes a storage slot and either adds or removes a certain amount from the number stored in that storage slot. And we also enforce overflow and underflow characteristics. So if your storage slot represents a balance and you debit 500 credits from it and you only have 400, that opcode's going to fail. So that's why it's called SCredit and SDebit, because it acts more like a bank credit and debit. So we put those opcodes, we encourage contracts to start using those, and then we wire those through into the state proofs to reflect when you're using the SCredit and SDebit operations. And we would need to add static writes and delta writes to the proofs to show when a transaction updated a field, not as setting a value, but as doing a delta change to the value, saying I added an amount and I removed an amount, not just that I set it. So to give you an idea of what sort of benefit we can see from these two changes, we need to step back a bit and look at that same transaction example that I set for the OCC example, and put it in the flow of a data dependency diagram. As you can see, a lot of these transactions have very few dependencies, and they flow very nicely. And what's interesting is if we change nothing in Ethereum today, we can actually get a somewhat decent example of isolated receipts. You just get rid of, if you're interested in transaction number 8, you'll need transaction number 2 and transaction number 3 because you depend on them. But the other 7 transactions, you could take them out and everything will still add up, and you'll still be able to prove that your transactions came from the right state and get the right outcome for the contracts that you're paying attention to. So that's what's great about the isolation of these, is you can still at least get it today in Ethereum. But not all of the transactions are as good as that. Let's say you're a coffee franchise and you decide you want to pay all of your employees on Ethereum. So you take your balance, you pay your employee, you pay your next employee, you pay your next employee, so on and so forth. You got 1 million employees. What happens if you're the millionth employee and you got over 900,000 transactions before you, and all you want to verify is that I got paid? Now you have to verify the payroll of everyone else in the company just because you got paid last. This is not really something that's really going to be useful to typical end users. I mean, block scanners and other things that aggregate all this data, they're going to want all that. But an end user only really cares about their accounts, and they only really care about who's sending the money if they have enough to send it. So this is where Delta writes unlock some of the potential problems that we have in parallelization. Delta writes will allow us to share the storage slots across parallel executions, where you can use the same storage slots in multiple sides and re-execute it in any order and still get the same results. So here's what happens today. Let's say A is going to send 200 to B, and A is going to send 100 to C. What you're going to see in Ethereum is you're going to read 500 and write 300 in A, see 0 in B and write 200 in B, and you're going to see in your next transaction 300 and write 200, and in C you're going to see 100 and 200. Now you can't change the order on those because you're not going to be able to read 300 if you already have 500. And the state proof consists of listing that like A has 500, B has 0, and C has 100. So it lists your start proof. So to get your actual transactional legitimacy, you have to execute the one prior to it to get your starting point. But if you only care about the deltas, you don't care about the starting point. What you're encoding is that A is losing 200 and B is gaining 200, or A is losing 100 and C is gaining 100. There's also one other tiny bit. You want to make sure that A doesn't get overdrawn. So that's why we need to put a little bit more information into the state proof. So in the state proof, we would say A has 500 and all the other transactional ranges have gone from +0 to -300 from that value. So if you get them in any order, A is going to always be within that range. Similarly, B has 0. The good news is B is not being debited. B is only being credited. Numbers only go up for B. And C has 100. Well, C could spend it, but C is not going to spend it. So C could receive 100. So from the state proof, when we encode the entire range of deltas that the field is going to have and the starting amount, something amazing happens. You can do these transactions in any orders, and you can actually get validity that the end state is going to be correct and it's going to be able to execute. So if your question is, my check didn't come through, why didn't it come through? Did my bank run out of money? Or am I on the OFAC list? Or did something happen with my smart contract wallet? You can execute that just on your wallet and not have to worry about the rest of the block. So basically, you take this isolated proof, and all the other transactions that might have been in this long chain of payments just fall away. You have your information you need to run it from the beginning, and you can get to the end, and it all proves there from the same cryptographic information that everyone uses. You just take the transactions in the fields you care about from that proof, and you can isolate it and get only what you need about it. So what's the end game for this? The time improvement, it's kind of a mixed bag. It is what the rest of your algorithm does. It's kind of orthogonal to whether you use OCC or block STM or whether you require strict access lists. So you get the speed up from the other systems that you would do before or during. The user impact is great because you only have to see your information, and the information that you need to download to verify just your transactions is much, much smaller. There is some downside though. This is not compatible with the current way that DEXs and automated market makers work. They need to keep updating that number in line to keep moving the market around. So if this were to be adopted, there would need to be some research done in the DeFi community to figure out if there's a way to get exchanges to work in a situation where the market maker might be shared across multiple transactions without being able to react to the other transactions in time. Sure, there's a way, just need to do some research on it. So to summarize, let me go back to this one slide at the beginning. I have an old copy of the slides here. So summarize the three sides to parallel transactions are infix, see, this is the problem with working offline with Google Docs, is it doesn't always get your information. So we'll just do this. So you have the prefix, the infix, and the postfix of where you put your information to make it parallelizable. And the real value in the users comes in what you do after the transaction and how you can deliver that value to that user. So I think we have the narrative wrong on Ethereum parallelization. The question that people are often asking is, how do you use parallelization to make Ethereum faster? And that's a great question because faster is almost always better, but we can go further than that. We can use parallelization to make Ethereum better, not just faster, but more useful and lighter on end users. Thanks.
just prefer a big presentation with lights because then you don't get as bothered. I'm just going to do light intro and let you talk about that. Trickle down. Hello, everyone. Here we have NYU Blockchain Lab. This is a breakdown of infrastructure from a research perspective. With this is Aisha Kiani. She is a facility professor and many other things, which she'll tell you about. And Suning Yao, who is a recent graduate. So take it away.
Hi, everyone. Thank you for your time today. So we will be going over through some topics that we've looked into at the research lab. Just for a quick background, my name is Aisha Kiani. I work at MNNC Group, which is a multi-strat hedge fund. And I also teach at NYU. I teach at NYU's School of Engineering. And over the years, I've had the pleasure of working with various students that have gone to develop projects and research, and Suning is one of them. So I'll give the floor to Suning from here on, who is going to cover all the projects and research topics that we've covered at the lab for past 1 year or so.
Yep. Hi, everyone. I'm Suning Yao. I'm currently a researcher at Aura, and I am a member of NYU Blockchain Lab. And I just graduated last year at NYU Tandon as an undergrad in CS. So for today's topic, we're going to cover all the different types of infra. For the first one, we're going to talk about network as an infrastructure. For example, L1, L2 blockchains, they are also infrastructure for developers because developers build smart contract on top of them. And also we got compute network and also storage network as the infrastructure because they provide compute power and also storage for data and computing. And also we have a different type of infra, which is protocol as infrastructure. For example, DeFi protocols, Uniswap lays out the foundation for all the DeFi trading activities. And also staking, restaking protocols, they are pretty new. It basically helps you to get involved in the network security. And also like NFT protocols, we have OpenSea's Seaport and also Blur. They have NFT trading protocols for developers to integrate. And also social protocols like Farcaster. And then we got infra for developers. So these are like the pure infrastructure for developers in their development lifecycle. For example, we got indexers and also rollup as a service and also hosting as a service. And then we got RPC provider as the endpoint for developers to interact with the blockchain, and also execution components, for example, virtual machines. So before we dive into the widely adapted projects and infrastructures from a research perspective, we want to show you guys some research exploration we are working on. So for the AI age of the current crypto space, we are actually missing a crucial crypto-based infrastructure right now. Because the problem is for the AI age, we need an infrastructure to solve these three issues. So the first issue is right now we have a lot of AI-generated content. Like Web3 platforms like Facebook, we have a lot of AI-generated images on those platforms because the account want to like increase their activity in the timeline. So they will post a lot of AI GC content. And then for the Web3 platforms, we also see a lot of bots. Like for example, a lot of trading bots. So that's why we need mechanism like proof of humanity to identify those bots and also the AI stuff. And then we got a lot of deepfake content. So for the deepfake content, it causes a lot of problems. Like for example, in the blockchain space, we got issues about KYC and also authentication. And also deepfake also introduce a problem of violation of a person's reputation. And then we have a final problem, which is about media data, because today's media always lacks authenticity, and also it's the history of the news and also images cannot be traced and verified. So that's why we need a crypto infrastructure to solve these problems for the AI age. So our experiment is called MPACS. We explore and tackle the problems with our research project of MPAC. We build an MVP that enables any media data and its processing logic to be verifiable on blockchain. We build it with a ZK virtual machine, and also inside of it, we have the media processing algorithm, and then we have the verifier on Arbitrum. So the general workflow is in the right graph. So first, user will use our front end to capture an image, and then our front end will attest this image. And also, another approach to import the media data is that you can access the media data from like a web page or other sources by cryptography-backed mechanisms. So after we got this import of media data, we can send this into our MPACS project. So MPACS project basically run inside of ZK VM, and then we have all those media processing algorithm as the program of the ZK VM. Then the program will take media data as the input and then generate a ZK proof and also compute over those media data. And then this ZK proof can be sent to Arbitrum stylus. We have a verifier contract here, and then it will be verified on blockchain. And also, it can make sure that the data and also the computation over those data is verified and trustless. So once it's verified on Arbitrum stylus verifier contract, it can make sure that it is forever verifiable because it is verified as a ZK proof and also is stored on Arbitrum stylus blockchain. And we're going to talk about some innovations of our research. So for the first point, we implement the full workflow of the implementation. We build out the front end for image input and capturing. And also for the ZK side, we build out the circuit and prover. And then we have the verifier. And we even have like an explorer for our implementation. So this is like a full workflow. And also we implemented some of the media processing algorithm in the ZK VM. It is very extendable to the full FF MPACS algorithm, which is a famous media processing library. And also for the last part, we implemented a Groth16 verifier on Arbitrum stylus. One thing special about Arbitrum stylus is that it is Watson-based, so it is not like the typical EVM environment. So we need to handwritten all the ZK verifier in Rust to make the ZK proof actually work inside MPACS. And then these are some challenges we met when we are building MPACS. So first, the architecture of MPACS is natively like more complicated than typical dApp. Because when you think about the typical dApp, you have like the front end and also maybe just a smart contract. And if it is a more complicated dApp, like a trading platform, it may also have the server. But for our MPACS project, we need to also consider all the ZK components. For example, we need to build out the front end and also the server and database for storing the image data. And also we need a prover for setting up this ZK circuit and generating the proof. And also have a verifier smart contract on the blockchain. And also because we are based on images and also media data, we also need a specialized explorer to show all those image data and also transaction history and all the transformation over those image data. And then we have another challenge in terms of the ZK stack choice. So we have several trays to build MPACS. For the first one, we can write out our custom circuit in a ZK domain-specific language like Circom or Cairo. but we didn't use this approach because it will take too much time to expand to the full FF-MPEG logic. And also the second approach that we eventually take is using the ZKVM, because for using the ZKVM, we can actually write high-level languages inside of this virtual machine to tell it to compile into ZK circuits. So this makes development much more easier and faster. And also we have some traces like ZK compiler, but it actually has more problems when we want to integrate the whole pipeline. So eventually we take the ZKVM path. And also we have the choice over the verifier. So ZK have a very minimum verification cost, but actually we also need to take consideration of the verifier choice, because we need to make sure that our application is scalable, that the verification cost can be minimum, and also if we extend to like a bigger platform, we maybe have like problems with the support and everything. So eventually we choose Arbitrum Stylus because it's more, it's actually more cheaper than the EVM, and also the Arbitrum blockchain is much faster, offering the faster finality and all the verifiable transactions. And then for the future directions, for the first one, we want to extend the features of our MPEG project. We want to support the full FF-MPEG logic. So right now we implemented 3 commands of the image transformation, but we want to expand to like 3,000 options and commands of the full FF-MPEGs. So it's basically like building a ZK EVM where you have like 100 opcodes, but for building FF-MPEGs into MPEGs, we need to like extend to like around 3,000 options. It's like 3,000 opcode. So, and then we want to achieve that use video as input. Right now, we only do computation over image because it has like smaller file size and it is a static image. So for handling video as the input, we need to handle larger file, and this will require continuation feature of the ZKVM. Because right now ZKVM only carries like 16 megabytes of memory, so it's extremely small. So we need to like break a video like down into different frames or like different parts, and then processing it with our ZKVM. And then we think about some of the use cases and platform and application of our infrastructure. So 2 of the ideas I think of is we can build a media rollup based on MPEGs. So we can have MPEGs as the core component to processing all the video and also the metadata computation. And then we can have this rollup as a specific purpose rollup. And then we can also have options to explore composable NFT. For example, we can have variation of CryptoPunks, or maybe we can like combine different CryptoPunks into a large CryptoPunk with like a pop art style art. And then after describing our research projects, we're gonna cover like some breakdown of the infrastructure from the research perspective. And these are all like widely adapted approaches. So for first, we can see that from last year, L2 space grows a lot. Like we actually have more L2s because at the first place, I think we only have like around 5 major L2s. But right now, if you look at L2B data, we actually have around 30 or 40 L2s. So the ecosystem is growing by a lot. And also we see more diverse forms in terms of the tag of L2. Like for the proof system, we can see there's ZK and also optimistic fraud proof system. And we also see a lot of like contestable rollup and also based rollup. And also some of the rollup are based on Celestia and also Bitcoin. So they are taking a sovereign rollup category. And also we see a lot of layer 2 on top of layer 2, which is layer 3. And then if you look at the graph on the right, you can see that we have more adoptions in the L2 space in general. For example, the Ethereum L2 TVL actually flipped other L1 TVL. So Ethereum L2 TVL is really big, and the ecosystem is huge right now. And we also see from a developer perspective, building a rollup is much easier. It is easier to bootstrap a rollup because we have tools like rollup frameworks and also rollup as a service, and even we can like one-click deploy the rollup right now. And then for the protocol as infrastructure, I want to talk more about DeFi. So we see a lot of like programmability into the DeFi space. Take one example is Uniswap V4 hooks. So what it essentially do is that every pool can be customized with programmable logic. So if you look at the graph on the right, you can see that if it is V3, it's just swapping the token. But if it is V4, you can have many like innovation and extension to it. Like you can build like better on-chain price oracle, or you can embed the entire token cell logic into the pool of Uniswap V4. And then another trend we see in the protocol as an infrastructure space is that we see a lot of intent-based architecture. So the idea of intent is that it aims for better user experience and better efficiency. So how it implements that is that they move a lot of the computation and also the components to off-chain instead of on-chain, so that they have more flexibility and also computing power to fulfill users' requests. We have seen a lot of examples of them, like Cow Protocol and also account abstraction and Uniswap X. And for the infrastructure for developers, another trend we see when we do research is about VM and compilers. So we see a lot of new ZK virtual machines coming out. For general computation, we see a lot of different flavors of ZK EVM with different type of proof system and EVM compatibility. Also, we see a lot of general ZK VM exploring the foundation with RISC-V architecture, WASM, or they even build their like own architecture set. And also for the compiler side, we see a lot of projects working on AI computation side. Like for example, we have zero-knowledge machine learning, which is ZK-ML. It essentially generates a ZK proof for the ML inference to make ML on-chain. And also we see like another approach called optimistic machine learning, which uses the fraud proof system just like Optimism and Arbitron to secure the ML inference on-chain. And that's all for the talk. Thank you.
We can take a couple of questions if anyone's interested, or yes.
You mentioned you're generating proof based on the video as an input. What exactly are you attesting? What are you proving here?
Yeah. So basically, we are proving the transformation over the image. So when we get the image data, it is actually attested by our front end. So that's why we are like capturing the image from the specific software. So it will like sign the image first, and then we take in this image into our ZKVM. Inside the ZKVM, users can perform some computation over the image, like flip the image horizontally, or increase or decrease the brightness of the image, and then we're gonna generate the proof of those images and also the transformations. So for having this transformation, we can have a trace of the history of this image being edited. So that's the basic idea.
Yeah, hi, great work. And I'm wondering what, would you like to introduce more about the architecture? For example, which ZKVM are you using and how's the benchmark? Yeah, thank you.
So for the benchmark side, actually for one operation, for example, increase brightness, it takes about 10 to 15 seconds to generate a proof. but it depends on the input size. Because if you have like a very large image, you're gonna perform the computation over like more pixels. So it depends on the image size. And also for the ZKVM, right now we are using RISC-0, but it is like we can use any type of ZKVM if we want to like switch to Succinct SP1 virtual machine, or maybe VDEM VM, or actually we can like use Cairo VM if we want to write the circuit inside of Cairo. So it is fully modular.
Great. Thank you.
Thank you.
Hello, everyone. This is Web3 Thrives, Pioneers, Challenges, and the Collective Vision. This is John Gleason with StormJ, and he's a COO. Thank you, John.
Thank you, JT. All right, everybody, thank you for showing up for the talk. You know, I know everybody who was out there walking in, just kind of smelling the air outside. I'm glad we're doing this in February and not July. Kind of smells a little bit like a new algorithmic staple coin out there, but it's just livestock. So I'm here to talk about what it's going to take for Web3 companies to really grow and break out and get real-world adoption. And I'm talking about mass adoption where Web2 companies are starting to use Web3 tech in real-world workflows. So what I'm really talking about here is like not just, you know, dabbling their toes, not just the innovation team doing a proof of concept or a trial or getting a partnership and doing an announcement and raising another round. I'm really talking about what's it going to take for the little tiny bubble there that's the Web3 utilization to be bigger than the other bubbles in that market. And a lot of projects, when we're talking sort of in our little sewing circles, right, we're all sort of focused on this set of what are the barriers to adoption? What are the big things that are preventing those enterprises, those SMBs, those individuals from taking this tech and really running with it? And from our perspective, what we've seen a lot of, it comes down to a few things, right? Everybody talks about wallet UX, but it's more than just the wallet UX. It's the user experience from end to end. It's really making sure that, you know, when we are building services, we're building them with a customer or an end user in mind, and making sure that we can hit those needs and solve those problems. A lot of the time, because it's a distributed service, it ends up being slow. It ends up being unreliable because it's all untrusted under infrastructure at the end of the day. And frankly, a lot of these things are the sort of the Rube Goldberg machine or a science project way of solving what is otherwise a perfectly well-solved problem in Web 2. But we have some ideas about what's actually working. Because at Storage, one of the things that we're really happy about is we are seeing really good growth. And part of our hypothesis is that we started with really looking at a market that we wanted to conquer. And it wasn't creating decentralization necessarily, although that was sort of the heart of the bottoms up is finding a decentralized way to solve a specific problem in Web 2. But really the why, the problem we were focused on was disrupting a market. And that market was Amazon S3, right? Object storage, the largest market for storage in the world. We wanted to find a way to bring all of those workloads into Web 3. And so if we think about our particular space, right, object storage, the outcome first, right? We wanted to find ways for customers to move off of the hyperscalers and onto Web 3. And what that means is we had to provide a value prop for them. We had to address what they care about most. And in the current market, we're seeing a lot of growth. It's because they care about reducing cost, right? Amazon bills are enormous. They care about privacy. They don't want their data being mined. They want security. And frankly, at the broader market, more people want to participate in the cloud economy that currently costs $1 billion if you want to crack that nut. And if we can limit the centralized dependencies of these services, all the better. But when we're doing these things and we're solving the problems and we're trying to build this use case, it's really important that the actual service that you build is good. It's got to be better than the centralized alternative or nobody's going to move. It's got to be cheaper. It's got to have broad-based applicability to a lot of different customers, and that's what's going to help drive that adoption, and that's what we're seeing as well. So in the storage space, that's one set of things, but we're also seeing this in a lot of other areas, right? We're seeing a lot of traction because cloud bills are high, and in this economy, people want to reduce their cost, and their highest element of cost, other than pretty much salaries, is generally their cloud bills. But there are other players in here, in kind of the deep-in space, that are also seeing really good traction. And these are sort of the players who are in the AI space, right? People who are in decentralization, they had built this pool of GPU, and all of a sudden the market came to them and said, oh, hey, we need GPU, and lots of it. And they were really well positioned to take advantage of that because they had built these distributed systems. These distributed systems are able to scale much more broadly and much more quickly because they don't have to worry about the supply chain issue of getting new equipment. They can get out there and tap into an existing market of underutilized resources and underutilized services and bring those to market quickly, much faster than anybody else who's just in the wait list trying to get GPU purchased. Similarly, if you look at something like LivePeer, LivePeer is doing a great job because they bring a service to market that looks and feels very familiar to your Web 2 buyer. But at the end of the day, it's all Web 3 on the back end. They have a distributed network of CPU and GPU that's doing all of the video transcoding. They have hosting services. They're actually backed by storage for the storage services on the back end. And we do all of the storage and the VOD on-demand streaming with LivePeer. But the key thing about looking at why these projects particularly are succeeding in a market where lagging adoption is sort of the norm for Web3 services is kind of key. So when you look at these three services and you look at what they're doing and you look at things like the Web3 index, which kind of tracks usage and utilization of services, you'll find that a lot of the players that are in the deep end space are at the top of utilization networks because they're solving real problems. They're solving problems for people that have money to solve them, and they do it in a way that's familiar and compatible. So I can talk a little bit about what's driving our growth and adoption. And by growth and adoption, what I'm talking about is we have real-world Web 2 customers migrating off of Amazon, migrating off of Cloudflare, Wasabi, Backblaze, mainstream products that are offering object storage today. We're growing anywhere from 40 to 50% month over month, bringing on real paid storage. And the way we're able to do that is sort of focusing on some of the inherent benefits of distributed systems. So we tap into 23,000 storage nodes in 105 different countries today. They're operated by 10,000 different individuals. In the aggregate, it's the size of a very large storage data center. And we built that by crowdsourcing it, kind of acting like the Airbnb of hard drives. And building that data center then gave us some really distinct advantages over the Web 2 providers, right? We're building this all on OpEx, not CapEx. We're not buying servers. We're not building buildings. We're not stuffing them full of hard drives. We're finding existing capacity that's underutilized that people want to monetize. And in many cases, it's fully depreciated. It's stuff where any money that gets made is absolutely attractive to the person operating it. But because of that structure, our costs are a lot lower. We don't have to worry about that stuff, so it affects our COGS. It allows us to price more aggressively. And in doing so, the entire network benefits, right? 22,000, 23,000 nodes all earning real money that's coming in from outside the ecosystem. From a speed perspective, when you have a distributed system, when you have those 20,000 nodes, you have all of that underutilized bandwidth available, it's incredibly fast from a throughput perspective. You can move a lot of data across the internet, and it can be fast consistently anywhere in the world. We don't have to build 10 data centers and replicate it 10 times all over the world. The network effect of having that huge distributed system gives you a performance advantage. We are globally faster than Amazon S3. Everywhere in the world, we are faster. And that's even with like a 5 meg upload download. Distributed systems are generally terrible with tiny files. But we are able to leverage that network of computers all over the world and be faster. From an availability perspective, every distributed system out there allows you to sort of take advantage of the fact that because you're pushing that workload around, if any component fails, it's not a big deal because you have a ton of redundancy elsewhere in the network. And so that gives us the ability to offer the equivalent of multi-region storage with a single upload, and it helps anybody using that service. And distributed systems kind of all have that in common, that ability to distribute risk across a large amount of networks. And because of the way that availability of all of those resources work, it gives you durability, right? It means, and durability means that if you upload an object, if you start a workload, that it's going to complete. It's going to be there and it's going to endure, as opposed to some of the maybe less structured things where if you have a single data center and that data center goes offline, like Amazon US East does from time to time, every service in the world that you love from Netflix on down goes offline with it. But with a distributed system, you kind of avoid that single point of failure inherently. Now, distributed systems and decentralized projects also, in addition to sort of exploiting the good things about their architectures, generally kind of avoid the successful ones, some of the harder aspects, right? So if your onboarding process is easy, if you simulate an experience that is familiar to Web 2 as much as possible, it's going to drive adoption. Those friction points of wallets and finding abstraction layers to solve those problems are absolutely critical to driving adoption. And that familiarity is really advantageous. If you have a compatibility layer, if you have things that are consistently compatible with the existing infrastructure that they have today, it's going to make it easier to adopt. They don't have to hire people with new skills or rebuild applications. It just works with with existing kit. And then not falling into ideological traps, right? Focusing on the customer. What do they care about? In certain ways, they'll care about a lot of the things like cost, speed, and durability. But buyers in the Web 2 world don't care about decentralization. And so presenting them a message that here it's decentralized, they'll respond they don't buy decentralization. But if they get all the benefits of decentralization, the speed, the cost, the availability, the durability, all those good things, that turns the meter for them. And so it's breaking into Web 2 has as much a messaging component as it does a feature and an interface. So the things that really move the meter for us, right, driving adoption from Web 2, is compatibility and performance. And this wasn't easy, by the way, because it's hard enough to build a decentralized service, let alone make one that's good, and then make it better than something like Amazon that's had a 15-year head start and billions of dollars to put into it. And so from our perspective, that compatibility layer, we put up an S3 gateway on the front. This is how all of the apps in enterprise talk. And it spoke a native Web3 protocol on the back end. We think of it kind of like as the Web3 mullet, right? It's all business up front talking Web 2 and party in the back talking Web 3. But a lot of this is actually also related to price. And it's not price in the terms of like token value or tokenomics or anything like that. It's really about price in terms of value, right? And being able to come in and establish a price point where ultimately enterprise will look at it and say, it's so inexpensive, I can't not at least take your meeting and have a conversation with you. And then once they see the value, being able to actually get real dollars in from Web 2 into a Web 3 economy is absolutely critical for scale, right? It takes it from a project to an ecosystem in which you can build businesses. And whole data centers can contribute a ton of capacity to an ecosystem and monetize it in a way that is material to their bottom line. And so when I talk about the Web3 mullet, when I talk about those interfaces, we talk about those in terms of like bridging those Web 2 and Web 3 worlds. And there's a whole bunch of benefits to the decentralization. There's a whole bunch of benefits to having sort of a minimum viable centralization, an interface that's familiar to Web 2. And it gives you those sort of two sides of the coin, right? That whole decentralization aspect gives you the privacy, the security, the immutability, all those benefits around performance, availability, data sovereignty, owning your own data, and the economics that really make sense for people when they're using it. But at the same time, you have a similar set of features in Web 2 that just the compatibility layer, that same familiar experience. And so when you bring those two things together, it really allows you to break out and break into that space. So what does this mean for decentralized services going forward, right? When I think of all of the services out there that are building applications and not the ones that are talking about any sort of transaction that could be in any kind of blockchain and cross-compatibility and all of that good stuff and composability. I mean solutions. I mean things that solve problems for customers that have money to pay to solve them in a differentiated way. I mean putting the decent and decentralized, like making them good. So compatibility is key, not just with Web 2, but a kind of across Web 3 as well. And so when you think about Web 3 today, and even over the last few years, it's still a lot of discrete individual services and point solutions that are composable into an application layer. But nobody's going to do that work, right? Everybody just wants something that's already a solution that works. And what we're seeing is, in Web 3, people putting together a bunch of disparate services into solutions, things that solve a problem. My favorite example is one of ours, so it's probably why, but our integration with LivePeer is actually an end-to-end solution that we're winning in Web 3. We take that solution to the National Association of Broadcasters event, the largest media and entertainment show in North America in Vegas. They'll be there next month. And we will take that application out there and we'll integrate with a bunch of media workflows, but this is a viable solution that is 80% lower cost than Amazon, just as performant, just as scalable, with an 80% lower carbon footprint. And you can take that message to a Web 2 audience and they will buy it. And when they try it, it's good. Web 3 solutions also have to be scalable. And not just scalable to the sense of like thinking in terms of like how many transactions per second will this do before the blockchain falls over. I mean scalable in terms of thinking in terms of what the Web 2 world looks like. So when I think of Amazon, I think of Amazon's 160 exabytes of storage. That's a lot. And for storage to store that storage on our network, we need 440 exabytes, right? We have an expansion factor where we're storing that on lots of things. That's an enormous amount of storage. And if we store normal data on there, I don't even know how many zeros that is, but it's also a lot. We need a lot of space. And if you're storing that on Filecoin the way to do it, they need a zettabyte. That's even bigger. So these are scales at which billion-dollar companies struggle to sort of get to that scale. Amazon is obviously the biggest. They are much bigger than Google. They are much bigger than Microsoft Azure, right? And everybody else is a rounding error. But Web3 technologies have this unique ability to tap into underutilized capacity all over the world and actually achieve bigger scale than some of the largest organizations in the world. And I think this is what's out in front of us. This is our challenge, is to provide those layers, bridge those gaps, bring those Web 2 workloads in to drive revenue success and ecosystem sustainability in Web 3. The innovation is all in Web 3. We are doing things differently. I look at our own project. We are the first net new architecture to try and disrupt Amazon since Amazon brought cloud to the market in the first place. Everything else has just been a Me Too carbon copy of their existing approach, trying just to eke out more and more narrow margins. This is a net new disruptive approach. It's like Airbnb disrupted the hotel industry. It's like Uber and Lyft disrupted and kind of wrecked the taxi industry, all for the better. This is an approach that we can take to existing cloud services, existing financial systems. Everything in Web 2 can be disrupted if we do it right. But we have to focus on the customer. Because even though the innovation is in Web 3, the workloads and the money today is still in Web 2, and we need to bring that into our ecosystem if we're going to succeed. So that's my talk. I appreciate your listening. Thank you. If anybody has any questions, you can ask me, or you can find me on Telegram, LinkedIn, Twitter, whatever your choice is. I'm surprisingly unoriginal across all three. Got a question in the middle, sir.
Hi, thank you very much for your talk. I represent Hivelo, which is a deep-in aggregator, and storage is one of the first protocols that we've integrated into our platform. Can you give us an update and snapshot of usage of storage, money spent, and what you expect over the next 12 months?
Sure. So if you want to kind of look at traction, revenue metrics, we're very transparent. So you can see revenue tracking on the Web3 index. You can see usage on storagestats.io, I think it is. But if you search storage stats and you search storage info, you'll get public dashboards that are maintained by other people that are pulling information about the network to give you exactly the size, utilization, full breakdown on egress, data stored, accounts registered, the whole 9 yards. So you get a really good footprint just on publicly available stuff. In terms of the next 12 months, we are relentlessly focused on providing a disruptive service in Web 2 and growing revenue. That's like job number one. So we are adding more compatibility. This quarter, we're bringing out S3 versioning, and following that will be object lock. And basically, once you've got that set of features with what we currently have today, we are immediately compatible with the two subsegments of the object storage market: media and entertainment, where we're rapidly growing in the media workflows for productions, and CDN origin. But this gives us a huge leg up in media archiving. And then in the second area, it's the backup services. And so today we work with most of the backup products today. But then there are things like Veeam and Haiku that require some specific features around object lock and versioning to achieve sort of their immutable storage for certain compliance use cases. So those are like the kind of product feature-wise. And then on the Web3 side, we're continuing to find projects to do integrations with that really bring well-rounded solutions. So we're working with Akash to bring together compute and storage. And that's been working well. We have a number of joint customers together, but we want to scale that up. We're going to continue to double down with LivePeer because it's just working really, really well. We have a lot of joint customers in that space. And it's really just about relentless focus. And so we have just a ton of progress in terms of enterprise offerings, achieving compliance requirements for large enterprises that need SOC 2 or whatever. So it's just, it's the boring stuff, right? Focusing on COGS, CAC, LTV, the SaaS metrics that really drive growth. And then all of that boring stuff really translates to rapid 50% month-over-month growth, kicking ass against Web2 companies, right? And that's what I'm really excited about. Hopefully that answered your question. Maybe a long answer to short question. All right, anybody else? All right, well, thank you very much. I appreciate it. With 16 seconds to spare, thank you. Have a great day.
Two minutes, nice. Test.
Yeah.
All right.
Hello, everyone. This is Inside DeFi's SEAL 911 team with Niv Iheskel, and he is the CTO of Hexagate. And we have Michael Llewellyn, Head of Solutions Architect at Open Zeppelin. Thanks, guys.
All right, thank you. All right, so I'll kick this off, and really quickly explain what is the Security Alliance and SEAL. So you might have noticed we're both from different companies in the security space, and there's many other security companies like us. We all have our own focuses. We work on different commercial projects and many ways we might compete for the same business. But there's a lot of common problems that this industry has faced for a long time in security that requires more than just individual companies trying to fight it. So the Security Alliance is an initiative that's been spearheaded by Sam Soon, who's the head of security at Paradigm. Many of you have probably been following him on Twitter. He is a well-known Anon who's been fighting for, and participating in a lot of security incidents over the last several years. And he, along with many others working with him, noticed a common trend that it was very difficult to create collaboration between different companies, between different entities. Often it was just working through people who you knew. And so over the last 6 months, nearly a year now, he has been working with many others to develop a nonprofit group called the Security Alliance that brings a lot of these companies together to serve and protect the Web3 community as a whole. So rather than having to focus just on my clients or Niv's clients or any specific barriers to helping someone when it's a broader community at risk, we now have a single group that can act for the benefit of the entire ecosystem, and there is plenty to do. We're going into a new bull market. Lots of security issues continue to be coming out. We had the hack with Seneca that happened very recently, and we are sure there will be more to come, despite our best efforts to try to prevent it. And we're going to have to be ready as a community, not just as individual companies or contributors. So that's what the initiative is all about. Sam, unfortunately, couldn't be here live because he is anonymous. So we are here in his stead to explain what we've been up to and why, if you are in the security community, you should be getting involved. So if you want to learn more, go to securityyalliance.org. But right now, we're going to break down the 3 initiatives and talk a little bit more about that. So before I jump into that any further, I'll give a quick introduction to myself and then let Niv introduce himself. So I'm Michael at OpenZeppelin. As you heard, I'm the head of solutions architecture, which means I focus on a lot of our biggest clients. I do a lot of security work with the Compound DAO as their security partner. And then we also do a lot of work with layer 2 rollups. We have a smart contract library that is very widely used, and sometimes we'll have security issues with people that use that library, such as ThirdWeb, which happened a few months back, where we have to ourselves be involved in a lot of community outreach. And then we also have a security product that we just revamped this last year, Defender. So lots of things and lots of things that might compete with others. And so from there, I'll hand it over to Niv to explain what he does at Hexagate.
Thank you. So I'm Niv, I'm the CTO of Hexagate and co-founder. Similar to OpenZeppelin being a security company, we're another security company in the space. We are providing real-time security and detection response for protocols, asset managers, chains, bridges, or basically anyone working with smart contracts in the space. We are working with more than 20 clients with the biggest names in the industry right now, protecting over a few billions of dollars at risk. And for us, as Michael mentioned, being part of SEAL 911 is very powerful, because also we are connected to this a lot of really smart people like Michael and his team and others that also help us to actually protect our customers even in a better way, and also the broader community.
Yep, thank you. So SEAL 911, that's the initiative that you've all been hearing about in the panel. So let's start with that, because there are 3 big initiatives that the Security Alliance works on, and SEAL 911 was the first and still probably one of the biggest impacts that it's had on the community. So if any of you are on Telegram, there is a bot that you can contact. It is literally SEAL_911_bot. And if you reach out to it, you can get in contact with a team of security researchers that include Sam, Forsaccio, and then also people from OpenZeppelin, from Hexagate, and many others, all potential competitors, but work together in this particular group headed by Sam Soon to work for common security issues that people might come to us for. So one example was over the last weekend, we had someone that came forward about a bug in a well-known protocol. There was no bug bounty for this protocol. There was no contact information this person could find. So the only thing they could do was turn to the 911 team and say, hey, I found this bug. What should I do? And what happened is, luckily, some people in the team had the right contacts. Like I said, in a lot of cases, it's who you know. And was able to get them in contact with that protocol team, get the bug reported, get it fixed, and then that person, even though there was no bug bounty, did end up getting a reward from the protocol for their efforts because SEAL 911 was able to represent the fact that this person had come to them to report it in good faith. So that's just one example. There's many others. Niv's been a pretty active participant, so love to hear examples from you.
Basically, as Michael mentioned, we're constantly getting tickets and people from the community surfacing out different types of things happening on the ecosystem. So another example, just recently, maybe a week ago, where someone found some vulnerable compound fork due to some vulnerability that was already known to anyone, but specifically this project was not aware, most likely, for this well-known issue. So this guy has been brought to the SEAL 911. Hey, I was trying to contact the team. I couldn't really reach them. There is this and that funds currently at risk. And the SEAL 911 really acted so fast. A few people saw the issue. Specifically, it could have been mitigated without white hat, without any really white hat activities, but rather a way to mitigate the issue. And I think this could not this could have turned for some malicious actor actually attacking those funds, but rather because this guy acted so fast and because the SEAL 911 people are always on, then we could really mitigate the issue and save a few millions of dollars just like that. By just communicating with the guy over Telegram and closing loops really, really fast.
Yep. And we all know Telegram is the lifeblood for all crypto communication, so that's where we ended up putting it. But I mean, the fact is that we've got over a dozen folks. There's a known repo on GitHub that lists all the contributors. And the biggest thing is that information sharing is really, really sensitive. If you found a bug, you have to be really careful about who you share that with. So having this common group of researchers who have committed themselves to not share information for their own commercial gain, to do exploits, to in any way misuse it, is a really important commitment to have so that when people turn to the SEAL 911 team for help, they know and can trust that they are going to be careful and trusted with that information and that they are going to be able to help. And in a lot of cases, it's just a fact of teams don't know where to turn, protocols don't know where to turn. We've had protocols that are being exploited, just not knowing what to do and need to reach out, all the way to, hey, I think my wallet has been scammed. I think my private key was lost in, maybe the LastPass hack, or my phone got stolen, or all these other things. What do I do next? How do I save my funds? Because in a lot of these cases, these hacks might be ongoing. There might be funds that could still be saved. There might be ways that they could actually report the crime that has been committed to the FBI or to certain phishing sites and actually get some of those funds recovered, or at the very least, make sure that other people who could be scammed are not going to be, because the word is out that maybe this link or this website is actually a scam and they should avoid it. And so there's also been a lot of work on phishing detection, where the team's been able to connect to Scam Sniffer, Chain Patrol, the MetaMask team, and Tay's also been a very good participant in the whole program, among many other people that I couldn't possibly list through, but they're all on GitHub, and if you want to give them thanks, then definitely give them a shout out on Twitter. So the team's been doing really good work. It's honestly one of the areas I haven't been as focused myself, but I'm always really impressed whenever I see a success story every other day about someone that really was helped that didn't have anywhere else to turn. And that's the whole point, is we have a lot of knowledge to share with the community, and it's really important for us to be able to actually provide that when they need it, and usually in the speediest way possible, because when hacks happen, speed is often the biggest factor in how many funds can be saved. So I think that's a good overall picture of that initiative, and that's one that I think we're going to continue to see a lot of support in, and we'd love to see anyone that wants to step forward and help. Again, securityalliance.org if you want to learn more and get involved. But the other initiative that has been going on almost as long is the SEAL War Games, which is really fun. It's more about prevention than response, and making sure that a lot of protocol teams, even the biggest protocol teams, are prepared when you have a security incident. And so Compound, which is one of OpenZeppelin's main security partnerships, was one of the first recipients of this. So we actually did a simulation where Isaac Patek, who's been leading up this initiative and doing great work, set up a mainnet fork of Compound, which basically means let's simulate everything going on in Compound, but on a separate private fork. Let's run all the monitoring infrastructure that you're using to detect security issues and see how that works, and then actually introduce a bug and a bot that will exploit this bug and see what happens. In this particular case, it was an Oracle failure. So, oops, the prices are being misreported. Someone's going to take advantage of that to start making trades to their advantage. How quickly does the team detect it? How quickly does the team figure out how to respond? And then how quickly have you resolved the incident, and how many funds are you able to save? So in that, I think we had we were able to detect the issue within a couple minutes of it occurring, or actually within like less than a minute. We're like, oh, we can clearly see the Oracle reporting bad prices. We can clearly see someone starting to exploit that. Ironically, the thing that took the longest time was not detection, but the response. And we knew very quickly what we should do. We should pause that protocol, that particular market and Compound, to prevent the loss. But then we have a multi-sig of about 4 out of 7 signers that need to show up and actually sign the transaction deposit. So getting all the multi-sig members to sign very rapidly in quick succession was actually the biggest bottleneck. Just a show of hands, how many people here have ever used a multi-sig or a safe? All right, there's a hand. And I'm going to guess, has anyone used it in an emergency situation where you had to sign it in less than a minute or two with multiple signers? Yeah, it's something that most teams, even some of the biggest teams in DeFi, haven't actually done before until they actually have to. And then that's the point where the timing really matters. So getting to do it in a practice environment where you actually see how quickly can you get to your keys? Are they on your wallet? Are they on a hardware device? How quickly can you plug it into the computer? Do you have your computer on you, your hardware wallet? Are you traveling? Are you in the right time zone? Or will you hear the notification where someone's asking you to sign up and sign that transaction? These are all the things that usually teams don't actually have a chance to think about until it's happening. So these simulations are a really good opportunity. And we took an overall response time of around 40 minutes, and we're able to cut that down to less than 10 minutes on average to get multi-sig signatures by introducing a pager system, rotating out some of the multi-sig members, and generally just practicing, hey, this is going to be the step that we take to quickly sign and quickly be ready in the future. And since Compound, they've also done a lot of simulations with both Aave and Yearn, who are very big protocols, have very good teams with security, but still having an outsider come in and put them in a situation where they have to respond and they don't know what's going to hit them is really, really valuable. And it's something that we definitely encourage all teams to do. And Seal continues to provide this as a service. If you go to the website, you can sign up for the waitlist to receive one of these drills for free. And it's generally gauged by how big of a protocol are you, how much of an impact on the community would there be if you were hacked and you didn't respond appropriately. But even then, a lot of the things that are being learned in these war games are being regularly published on Notion and other resources so that other teams can learn, how can I run simulations, how can I run monitoring. So I know on the monitoring side, Niv, this is Hexagate's bread and butter. Just generally, what are the things that a lot of teams aren't thinking about with monitoring or are just really important to think about when you might be setting up a war game?
Yeah, so I think also to add on what you mentioned about around instant response and having a really precise roles and responsibilities when an emergency happens. Every now and then also the CLN 111 members participate in war rooms where really protocols are not prepared at all whenever something big hits them. And then it's one of the most chaotic things you can really participate in. People just do not know what to do, trying to contact exchanges because maybe the attacker would deposit some funds into the exchanges, try to contact Circle to freeze the funds, and so on. Lots of different kinds of ideas, in which if you are not prepared upfront, then you really don't stand a chance. Back to the question or monitoring. So basically, the mindset that we have when we protect the protocol as Hexagate or part of CLN 1, literally the same mindset where we first thing is kind of map all the threats in the protocol, understand how where exactly are we expecting some failures to happen, for example an Oracle deviation or some bad Oracle updates, whatever, or just generally in the contract audit might have missed a couple of bugs, which is completely because audits are not enough to cover any type of bug. So when we work with protocols, for example, we set up monitors for anything really that might fail, which is also monitoring which is based on machine learning that tries to detect unknown threats and also like the known threats, like any administration changes due to maybe like private key theft, any like deviations in oracles and so on. Once we have all the the detections in place, then we start working on instant response, where we do this tabletop exercise. We set up roles and responsibilities for every personnel in the team, who is in charge of comms, who is in charge of like triaging the bug, who is like the one responsible for sending like or even automating some action such as pausing the protocol and so on. All in all, like only after you have this full-blown detection and response, only then we believe that then security is really achieved, because with just detection itself, as Michael mentioned, you have the best detection, but then 40 minutes later you try to assemble all the team from all the time zones to sign some transaction. Obviously it doesn't work, so you have to notify them, keep them in the loop with some pager or something. And also on the other side of the response, like you must have like very clear steps on what you're gonna do just besides detection. So it's kind of a combo of both detection and response.
100%. And best way to know for sure is to run through as realistic a drill as you can with maybe even a few team members not knowing it's a drill. All the better. So with the time they have left, we'll talk about the last initiative that has recently come out from the Security Alliance, which is the White Harbor Agreement. Now, I'll say that we've already talked about, your prevention, which is ideally having run through these scenarios and being prepared. When you maybe find a bug or, are trying to figure out how to fix it, maybe going to SEAL 911. But there are some scenarios that have come up, such as with the Nomad hack that happened a year or two ago, where a security researcher might come across a bug, and they might be in a situation where they know that bug is going to imminently be exploited. And their only options, at least in their mind, are either I can let it be exploited and let a black hat steal these funds, or I can act to exploit the protocol myself to safeguard the funds and then give them back to the protocol. Now, that is a very dicey proposition from a legal, ethical, just make sure you get it right sort of perspective. However, these are things that have come up, such as with the Nomad White Hat exploit, where a lot of people in the community were coming forward to help to save funds. And then in other cases where you've actually had maybe a transaction in the mempool that is about to exploit the protocol, so maybe you can front run it to safeguard the funds in that way. So these are very specific examples. They definitely don't apply to every scenario, and in many places it's probably better to report a bug rather than white hat exploit it. But for those scenarios, what the Security Alliance has put together is a White Harbor legal agreement that allows a protocol to publish a legal document that says, if you follow these procedures, we will consent to you white hacking our protocol to safeguard funds, and you may send them to this recovery address specifically. So, I'm not a lawyer. No one on here is, but this is a legal document that is available and is currently going into open review with the community to receive feedback to see what protocols might be interested in implementing this and what white hats might be comfortable exploiting protocols in these very specific scenarios with this agreement in place. So we're currently collecting feedback on that now. I'm very interested to see what comes, but I think the most important thing there is just making sure we have as many tools as possible, and that even if we get to a scenario where a white hat is necessary, we've done everything we can beforehand in terms of getting, doing good testing on the code, getting good audits, getting good monitoring, getting good incident response policies, all the way down to, okay, there's now these very specific scenarios where a white hat might be necessary. So in all, the purpose of the Security Alliance is to work on all these initiatives simultaneously to better have really defense in depth for security across the community. And a lot of this work is coming from different places. OpenZeppelin, we feel very confident about our Solidity and smart contract auditing skills. Hexgate is very good at real-time monitoring. In some cases, we might be competitors, but within the Security Alliance, we can work together and pool our resources, along with dozens of other great security researchers that have already put in a lot of effort and saved a lot of funds and helped a lot of protocols sleep better at night. But at the same time, it comes down to everyone's individual effort and making sure that we collectively make the best use of it. So that's for the most part the remainder of our time. If you are interested in getting involved, or if you want to make use of any of these resources or in any way learn more, go to securityalliance.org. And that is a great place to get started. We're always looking for feedback. We're looking for new members to get involved, to help contribute their security knowledge, and to just tell us how we're doing and how, what are problems in the industry you want us to be focusing on next. So Thank you all for your time, and yeah, we hope to see you at the next one.
Countdown on there to when you start, and or watch for them actually. They'll signal you when you start. It'll be about 4 minutes, 3 minutes from now.
Okay.
And then I'll give you a countdown on that for each one. Okay.
Now? Hello, everyone. My name is Dorothy Roche. I'm on the ERC 4337 core team, and I'm here to talk about what's new with ERC 4337 with account abstraction, and what we've accomplished in the past year and moving forward. So exactly 1 year ago here in Denver, we announced on stage the mainnet release of ERC 4337. We just passed the security audit pass then. Since then, if we look what happened since then, so we can see in traffic, we see that now we reached some in the vicinity of 2 million transaction or user operation per month. We've reached over 700 monthly users using account abstraction, which I believe it's quite good for the first year. We've seen a lot of activity with our partners on the network. We have like great. It's left slideshow. We've seen a lot of activity. We've seen 27 wallets and SDKs active, open source bundlers that you can download and use, our own reference bundler and many others, multiple servers, bundlers as a service and paymaster as a service available on the blockchain, block explorers. A lot of traffic is done there. We also released many grants. Many of those SDKs and bundlers and the Block Explorer received grants for doing things around account abstraction in ERC 4337, doing different signature schemes, metric dashboards, accounts, etc. Very interesting is to see that this is the actual gas pay by paymasters. We see that 95% of all user operations, of all transactions were sponsored, which means that the idea of having a sponsor paymaster really kicks in. Users like the idea of using a simpler service than using native tokens for paying gas, and paymaster play a great deal doing that. So, these are several of the EAPs ERCs and EAPs that surrounded the account abstraction. We have modular wallets led by Alchemy and by Rhinestone, pushing standard modular accounts standards 6900 and 7579, using a popular signature scheme that's available on each phone, passkeys and WebAuthn, which is a EAP 7212, and ERC 6492 for allowing signing transaction, signing messages even before your account exists. This is something that basically missing from contract accounts. Now accounts just like on par with the EOAs can perform signatures. Pushing forward, we are working very hard with our partners to having the mempool, the P2P mempool, several bundlers already supported with the previous release that we released a year ago, which is called entry point 0.6, 0.7, which was just released. We'll move forward, and we stay tuned. We're about to release it next month in London. About our releases, last year we released the version 0.6, and with each version we are trying to make it more secure. We're all everything about decentralized accounts, and so the entry point has to make sure the network is secured. So version 0.6 was all about making transaction and hashes available to all the tools around them. Version 7 again pushed the simulation and the security of paymasters, and also we move one step forward towards a native account abstraction, which we'll see shortly. Now, if we try to look what we are pushing, the way forward, the way we see it, we have the protocol front, the puzzle. There is the ERC 4337 itself, which becomes more mature with version 0.7. We just passed the security audit. We extracted the core validation rules, the complex part that define how the mempool is kept decentralized and secure, into a separate ERC. And we started to work on the native account abstraction, ERC 7560, and make sure that it is aligned with the 4337. More about it later. On the networking front, we are continuing the work in the maintenance of our reference bundler and mempool as we've seen, and trying to push a different chain to adapt the network. It is more than just running a bundler on a network. In parallel, we are working on implementing a guest fork to support the native account abstraction. This is still not available. There is no chain that currently use it. But all the work that we have done both in bundlers and accounts and paymasters will work towards both the ERC 4337 and the native account abstraction. On the account front, we've seen a lot of work, as I said, by Alchemy pushing 6900 for module account abstraction, and another standard for module account abstraction, 7569. We try to help them moving forward in the various specific ERCs we've seen earlier to support those accounts. On the paymasters, all of the paymasters we've seen, most of the paymasters we've seen earlier, are all paymasters that work with an off-chain signatures, what we call verifying paymaster, which actually it's a way that the paymaster takes a user confirmation to pay off-chain and makes this validation on-chain. We are moving forward to push to improve the standard, to have better support for token paymasters, which are completely on-chain, decentralized, to allow you to use tokens. I want to stress more about, I mentioned several times, the native account abstraction. First of all, native account abstraction, we call it an RAP, which is it's not an EAP, it's a roll-up improvement protocol. We understand that native account abstraction is something that will start with sidechains. Actually, innovation in general starts more with sidechain. And with the understanding that mainnet is less innovative and and more secure, the idea is to push new features into roll-ups first. So we started an initiative we called RAP, which is roll-up first. And actually, EAP 7212 for supporting passkeys is passed as an RAP, which means it is not something that is expected in the near future on mainnet, but it surely will be accepted first on roll-ups and sidechains. We also pushed the native account abstraction as a roll-up, as an RAP, to be accepted by roll-ups. Now, what is RAP 7560? In short, it is an enshrined version of ERC 4337. It is built from ground up in order to be interoperable with the 4337. If we think why we are trying to push it, because we're already seeing that several L2s are pushing their own versions of ERC 4337, like Starknet and ZK-Sync. They are built on the architecture of 4337, but each one of them made some modification. These modifications make them incompatible with 4337, which means it's going to be very difficult for a wallet to support both standards. With this understanding that we need something that is compatible, that to allow modular accounts to support both native and ERC 4337, we started to work on 7560. And as I said, it's not something that we think will go to mainnet soon. We want to see it on L2s first. What does it give of us? First of all, as I said, it is compatible with 437 in that it's going to be quite easy for account to support both. It has lower gas fees. It reduces the overhead of having the entry point as a contract because it becomes part of the protocol. It supports, in the long term, it will support migration from EOAs. This is something that is very much anticipated, and everybody asks us, how can we use ERC 437 with EOAs? And the answer, of course, is right now it is impossible. But with 7560, it will be eventually possible to migrate your account. It supports some security features like inclusion list. And almost most importantly, it means there is a network commitment. There's a network that accepts a native account abstraction means that it expects, you can expect the network to support it. If there is a problem, like there is in the network, you do expect, if needed, the network to do what it need to save the user funds if there is a problem in the accounts themselves. I moved a bit fast, so. Anyone has any questions? Okay, thank you.